Okay, folks. So it's just 9 o'clock, so we'll start the process. So firstly, welcome everyone. Thank you all so much for coming to this workshop. I believe it's the first of its kind anywhere. So this is really exciting. There's a lot of interesting stuff to talk about. So first, a couple of things. If you're giving a presentation this morning, if you can download your files to the Dropbox, so you should have that link in your email, and add those slides, you can play them off of the live pad up here. So firstly, thanks to the CCA for facilitating this. It's been really seamless. It's fabulous. Enjoy the hospitality. Thanks to Mordecai for pushing for this. Phil and Yuri and David for supporting what we're doing here. And thank you for coming along. And hopefully we'll have a really interesting conversation over the next 3 days. Okay, so why are we here? For a variety of reasons. LIGO is detecting a large number of stellar mass black hole mergers, as we know. They seem to be overmassive. And the cartoon picture that we have is something that looks like this. Hopefully by the end of the workshop we'll have a better picture than a cartoon that I've put up here. But the idea is basically at the center of a galactic nucleus we've got a supermassive black hole. We have a swarm of angry bees going around the central queen bee, so we've got stellar mass black holes orbiting at various angles. And if you throw in a gas disk into that, you generate an active galactic nucleus. And some fraction of those stellar mass black holes in the galactic nucleus will end up in the disk just with geometric arguments. Another fraction will get ground down into the disk. And so if you're interested in a place where we can accelerate black hole mergers in the universe, these are good places to look. Okay? So if you have that picture, then you can generate a prediction for a rate of black hole mergers depending on what you think an AGN is, what your binary fraction is, the rate of occurrence of AGN, the number of black holes, stellar mass black holes that you expect in the galactic nucleus, and sort of how efficient the whole process is. And so you can generate a rate estimate. All of these parameters are pretty darn uncertain. And that's part of what we're going to be talking about here over the next 3 days. Right? So it could be that a lot of these numbers are on the large side. Right? I think it's unlikely, but it's possible. In which case, a large fraction of the mergers that we're seeing with LIGO are coming from this channel. Okay? In that case, I'll put on my optimistic hat. Right? You don't need to know anything about baseball or New York sports teams, but basically this hat is worn by people who expect to win every game. Right? So if I'm wearing this hat, then I expect that these numbers are pretty high, and that we get a large rate of black hole mergers in AGN disks. If you wear this hat, then you expect that this channel will produce a lot of mergers, a lot of black hole mergers. If that's the case, then we learn some things about AGN disks. A few of us in this room get some personal satisfaction at having predicted that LIGO would see overmassive black hole mergers. But I would argue that actually we should wear a pessimistic hat. So this is the hat of the New York Mets. They suck. If you wear this hat, then it means that secretly you expect to lose most games, right? So you're a pessimist. So if you're wearing your pessimistic hat, you expect that somewhere something is going to go wrong in this, right? We're missing something. You know, some number is wildly overestimated, or we're just missing something, missing some physics that we haven't really thought of. So if you wear this hat, I would argue that actually we get more constraints on AGN disks from LIGO than we can from electromagnetic results right now. The reason for that is because I have a sophisticated model of an AGN disk right here. It's color-coded. So the hot bit is here, it's blue in the middle. The cooler bit is red on the outside, and sort of it's a multi-color disk. It changes aspect ratio with distance from the central supermassive black hole. And this thing can have an effect on our models of galaxy formation. It seems to play a role in lambda CDM. We think it plays a strong role in lambda CDM. So right now, electromagnetic observations are basically allowing us to test models of the photosphere of these things. LIGO is, for the first time, allowing us to probe within the AGN disk. So we can test the density and lifetime of these systems. And so if you wear a pessimistic hat from this channel, if you say that something is going wrong, we actually learn more about AGN disks. And you win, okay? So our goal at this workshop is to figure out what hat you would rather wear. I understand if you're from Boston, you can't never wear this hat. But we can replace it with a Boston Red Sox hat, that's fine. So essentially what I'd like us to do over the next 3 days is think about what you would want to see. What work we need done in various fields in order to choose between an optimistic hat or a pessimistic hat. Or maybe we end up somewhere in between with a, I don't know, Kansas City hat. All right? The goal of the workshop is, first day in the morning, we're gonna outline the problem, the various aspects that feed into the problem that we're thinking about here. So we're very much like the blind folks who are trying to figure out what an elephant is. We have some experts in this room on the tail of the elephant. They're going to tell you about the tail of the elephant. We've got some experts in the room on the legs of the elephant. And they're going to tell us about the legs of the elephant. We also have some trunk experts, some ear experts, and the side of the elephant experts. And hopefully we can put it all together so that by the end of this morning, we'll have an outline roughly of what the elephant is, right? Or maybe where it's broken, okay? So if you have slides to present this morning, if you can please download them to the Dropbox. We're going to have 20 minutes per session, per primer. Keep your questions till the end. We'll have about 5 minutes in between these little discussions, these primers, where if you have general questions, you can raise them then. And then we'll get the next people up to set up for their presentation. So these are going to be the longest talks you're going to hear all through this workshop, 20 minutes max. We're aiming for conversation in the discussion session, so please send your one slide to the session that you're interested in, sort of joining in the discussion. So Benza has already got a bunch of slides for this afternoon. But if you've yet to contribute something, please email him your one slide. Likewise, Zoltan, Mordecai are right here. Jillian and Sada can also take your slides for those sessions. All right. So when we have our discussions, the goal is that the chair will basically present your one slide, and you can talk about whatever it is you want. You can advertise your work. You can advertise someone else's work. You can raise a question that you think hasn't really been considered or should be considered. Whatever it is, please contribute your one slide and email the chair of the discussion session. Okay. So for our speakers this morning, my phone is going to make an obnoxious noise when your 20 minutes are up, and then that means I will stand up and come and be obnoxious to you, okay? And so if you can please hold your questions for after the 20 minutes, so we get a rough intro to each topic, and then we'll move to the next speakers, okay? So I have a few minutes left, but that's okay. Any questions about just the general format or anything else? If you feel, by the way, if you're speaking, if you feel particularly optimistic or you feel particularly pessimistic, please go right ahead and wear the hat that you feel is appropriate. And please tell us why you think you're pessimistic or you're optimistic, okay? So please use these. Okay, I'll leave them up here. You can. They warned us against that, but yeah. Okay, sure. Yeah.
He didn't put a straw.
Right.
Irish spelling.
No, he's not. So Ben left.
Well, I mean,
So for fellowships, are you interested in like stuff about an area?
I thought that's very good. There's a possibility that I mean, it's fun. That's Syracuse.
Are you going to try and put it on the?
We're looking at like Columbia Bridge.
So Janet.
Oh, no. Sure. Okay, yeah. 5259, yeah.
But yeah, so.
In October.
Okay. So we're not warm?
Yeah.
That's not. Yep.
I feel like he got this job because he didn't, he never worked a bad job.
Well, so those two are right. If you're at
Yeah.
Please put your slides and talks in the Dropbox, which is linked from the website.
Doesn't work for me. I can't upload.
Is
we can't.
Yeah, I can upload. Okay,
Okay,
that
I
I will
need
go
to
chase.
figure out.
Barry?
Yeah.
Barry.
Yeah, okay.
Can I start talking now?
Yes.
Only 20 minutes?
Yeah, you have 20 minutes. So, okay, folks, our first speaker is Kaya Mori. He's going to talk to us about populations of objects in galactic nuclei, in particular in our galactic nuclei. Okay?
So, good morning, everyone. I'm going to be talking about our recent discovery of X-ray binaries in the center of our galaxy, and this work was presented in our Nature paper last year. We have some continuing work which I will present. I have a paper coming up in a month or two. Everything I need to talk about will be in that paper.
Oh, sorry, yeah, use the mic. Yeah.
Hello?
Yeah, that's
Yes, so everything I will talk about will be in my paper to be submitted to UpJ in a month or two. So let me start with some big picture. So our Nature paper work is a part of the big observation program which we have been running with a new star. So I will start with Chandra's X-ray view of the galactic center. This is 2 degrees along the galactic plane, and then 0.8 degrees across the plane. That's the Chandra X-ray image, and you can see all these green dots. These are all X-ray emitting point sources. So Sagittarius A star is in the center. You have more point sources there just because there's more stars and binaries, and also because Chandra spend more time, multi-million seconds in the center, so you have more exposure time. That means you can reach out to fainter sources. So we started with these 3 big questions, and then we followed up this same exact field with new star, which you can see in this yellow rectangular regions. So the first question is, we have 9,000 Chandra sources in this field. What are these sources? So the short answer is they're mostly magnetic series with white dwarf. And the second question is, new star discovered hard X-ray emitting diffuse emission near the center. It's about 4 by 8 parsecs. That was a discovery about 20 keV, which previous hard X-ray telescope couldn't reach. And then later on, we figured out that diffuse emission is an unresolved population of a bunch of magnetic CVs. Particularly, it's an intermediate polars with a 0.8 solar mass, white dwarf mass on average. And if you go down to the center, in the center parsec region, that's the topic of my talk. And what's the source population there, and emitting some X-rays there. So the center parsec region has been very interesting for the last decades. Especially, can you find some Barkov cusp of stars and X-ray emitting point sources? And it's also important to gravitation wave detection, like we're going to be talking about today. And then where are these radio pulsars and millisecond pulsars? We discovered 1 magnetar in the center. Do we have more? And the really interesting question is, where are these black holes in the center parsecs, as predicted by some papers, including most recent ones by Genizorov and Zorgen and Kosis. I think Dr. Kosis is here. Hi, nice to see you. Okay, so we have been running these 2 major approaches for detecting X-ray binaries in the center. The first approach is, like I said, Chandra telescopes spend multi-million seconds looking at these hundreds of sources in the center parsec. So we're going to look at each of them and then characterize its X-ray spectra and then timing information so we can identify them. That's one way. And the other way is some of these X-ray binaries outburst occasionally. Just the X-ray luminosity goes up by many orders of magnitude, which was also detected by a Swift X-ray telescope monitoring the galactic center every day. And then we followed up these transients by a new star and Chandra, and sometimes infrared and radio. So that's going to be adding more X-ray sources in the center. So there are 2 approaches we are running. And what are our targets? So mostly these X-ray point sources are powered by accretion. So we are talking about LMXBs, high mass HMXBs with black hole and neutron stars, or magnetic CVs. There are many of them. Or another class is called a millisecond pulsar. It's rotation powered. So these are our targets. And there are various ways of distinguish between these guys. For example, using luminosity or spectral shapes or variability. I'm going to go into more details later on. So especially, there are many magnetic CVs against some LMXBs. So how do you know which one is which? So this slide will show you 2 contrasting X-ray spectra. On the left, you can see a persistent neutron star LMXB in the galactic center, and X-ray spectrum starting from 2 keV up to 40 keV by adding new star data. It's a nice smooth continuum with a soft photon index around 1.5 to 2. On the other hand, magnetic CVs show something different, which is a much harder continuum and a clear ion emission lines. So this is one of the information we are going to use to say, hey, that's LMXB is a black hole and neutron star on magnetic CVs. Okay? Then we started this work almost 3 years ago, looking at the galactic center. So this is a zoomed-in image of Chandra's, of the Chandra sources. Again, Sagittarius star is somewhere in the middle. I think this is a 4 parsec radius. You see hundreds of standard sources. And we started using 1.4 millisecond ACIS-S observation first, and we published a paper last year in Nature. And our continuing work is actually analyzing more data from ACIS-S for 3 million second observations. And then, just to be conservative, we presented 93 brightest sources in this field with net counts about 100. So make sure we can measure the spectra and light curves very well. So like I said in the 2 slides before, hardness ratio is a key. Because some sources are not bright enough to give us enough counts to give us a nice looking spectra like you saw 2 slides away. So we started classifying all these sources based on the hardness ratio. So in y-axis, you can see harder continuum sources like magnetic CVs, and softer sources down as a function of radius, distance from Sagittarius star. So farther away from Sagittarius star, you can see hard sources consistent with magnetic CVs. If you go into the center, below 1 parsec, you can start seeing some magnetic CVs and some softer sources. So you see some 2 populations here inside 1 parsec as opposed to outside 1 parsec where you see mostly magnetic CVs. So if you have enough counts for each source, you can just look at the spectra. So this is a soft source which appears to be a nice parallel soft sources in the 2 different observations. This is ACSI and this is ACSS. You don't see any ion lines. On the other hand, if you pick a bright hard source, you can see hard continuum and clear ion lines, just like this. So that's magnetic CVs. This is neutron star or black hole LMXPs. Okay, so when we expanded the analysis of ACIS-S data, we found another source which has soft non-thermal spectra like this, and its light curve shows some nice variability here over the last 12 years or so. So if you, okay, one more slide. So for the fainter sources, what we can do is we can just stack up, let's say 12 faint sources, and then make a combined spectrum. So again, this is a soft sources stacked up, looking like a nice parallel source. This is a stacked up hard sources, which will give you a hard continuum and a very prominent ion lines. So that's how you can identify a group of sources between hard and soft. So if you put together soft non-thermal sources in blue, they are distributed like this around Sagittarius star. Sagittarius star is here. It's a 1 parsec radius circle. And then hard sources, which are magnetic CVs, they are spreading out like red points all over the place. And this non-thermal source distribution is actually mostly aligned with the galactic plane. I'm going to come back to this later on. So I'm just showing you our timing analysis results. So out of the 13 non-thermal sources, we detected 9 of them are variables, as you can see in some light curve here. So what are these sources? 13 soft non-thermal sources. So like I said, 9 out of 13 are variable. So they are not millisecond parsecs. So usually millisecond parsecs spinning at millisecond. Otherwise, at the longer time scale, they don't really show variability. They're a very stable system. So these sources are likely neutron star or black hole LMXPs. Other types are ruled out. I'm not getting into the details here. So the question is, which one is it, neutron star or black hole LMXPs? So to answer that question, I'm going to talk about the X-ray transients first. So away from the Chandra program, Swift XRT has been looking at the galactic center every day over the last 13 years. So they never missed any outbursts down to 10 to 34 per second. That's a very faint end of X-ray outburst. On the other hand, if you look at elsewhere in our galaxy, including globular clusters, there's no such program. So you may be missing some fainter X-ray outbursts. Okay? So there is something called the VFXTs, standing for very faint X-ray transients. Their peak X-ray luminosity is actually below 10 to 36 Hz per second, down to 10 to 34. Swift program of looking at the galactic center discovered 9 of them. Okay, so this is something new people have been interested in over the last decade. So that's nice progress in the galactic center. So back in 2016, the same SWIFT program found 2 new X-ray transients in the galactic center, right next to Sagittarius star. So these 2. NuSTAR followed up these 2 transients, and we characterized their spectra and light curves. So first of all, these peak X-ray luminosity is about 10 to 37 Hz per second, so that's a bright end. We didn't detect any pulsation or type of X-ray burst. And there's no X-ray outburst detected from these sources in the last 20 years. And we found no counterpart in the Chandra catalog. That means in a quiescent state, these transients are very, very faint. So let's look at some X-ray spectra from NuSTAR. That's 3 to 79 keV. We got many photons. When we fit the power law model, you can clearly see nice broadened ion line and also asymmetric around the black hole and neutron star. And also we detect the QPO at around 15 millihertz. So these are the typical characteristics for the black hole transients and also neutron star transients. So it's hard to distinguish between which one is which, just from this kind of data, unfortunately. So, like I said, Swift, XMM, and Chandra has been looking at the galactic center over the last 20 years. They discovered many transients. So let me go through this chart. So this is the number of transient as a function of distance from Sagittarius star in parsec. NuSTAR discovered 1 magnetar. 5 of the VFXTs are in the central 3 parsec, and we have 3 transients, which are probably most likely black hole transients. Otherwise, there are 6 confirmed neutron star MXPs with type of X-ray bursts or pulsations. So in red, they are spreading out all over the place, up to 50 parsecs. And let's talk a little bit more about VFXTs. So, like I said, 5 VFXTs in the central 3 parsec, they had multiple bursts in the last 10 or 15 years. So they have recurrent outbursts. On the other hand, 4 VFXTs, these guys, just outbursted once. And our speculation is maybe these 4 VFXTs had multiple outbursts, but they are actually outside the most sensitive region of the Swift telescope, so we probably missed them. So we think all these VFXTs probably had multiple outbursts over some years. And if you look at the local VFXTs, 7 of them have been identified as neutron star MXPs. There is 1 known black hole VFXT, which outbursts twice, but there's 1 caveat. I think the distance is unknown, so if you use a larger distance, it may not become VFXT. So Sears actually speculated VFXTs have a low accretion rate. That's why X-ray burst luminosity is actually lower due to the smaller accretion disk size. One possibility is that they are outer compact X-ray binaries, or if it's a neutron star system, strong magnetic field can truncate the disk like a propeller effect, then accretion rate goes down. So combining all this information, we know probably VFX is a neutron star MXPs, in my opinion. So let's look at how often outburst happens for black hole systems and neutron star systems. So like I said, 6 neutron star MXPs in the galactic center, they had a recurrent outburst. At least 5 VFXTs had a recurrent outburst. If you look at the local neutron star MXPs, 7 out of 12 did outburst multiple times. And other guys are probably VFXTs with only 1 outburst. Other guys are probably missed. On the other hand, if you look at the black hole transients, then they have a very long recurrence time. 43 out of 59 had recurrence time above 50 years or longer. That's what you see here. So I just want to mention that there are some outliers. One neutron star LMXP 10X4 didn't outburst since 1970s, or we have a famous black hole LMXP which outbursts multiple times. So there are some outliers and great one. So going back to the same histogram, number of X-ray transient versus distance from Sagittarius star, now I'm putting in some reasonable assumptions. Then again, 6 come from neutron star LMXPs, 9 BFXTs, and they're all in red. And I'm speculating they're neutron star LMXPs. So that's how they get distributed. On the other hand, 3 transients, including the 2 transients in 2016 I mentioned, they had only 1 burst in 20 years. Okay, unlike these guys with multiple outbursts. And going back to my Chandra source analysis, like I said, there are 13 quiescent non-thermal sources, but they never outbursted over the last 20 years. So based on the information I talked about, I would speculate these guys are also black hole LMXPs. And then they're all sitting inside 1%. So there's a spike here in black, and there's a 1 magnet hour. Okay, so right now, there are about even 15 neutron star, 16 black holes, but that's not the whole story because we may have some hidden LMXP population. Number one, if you look at the globular clusters, there are many neutron star LMXPs with a low accretion. They just give you thermal emission, but not non-thermal emission. These guys will be undetectable in the galactic center because we have a higher absorption by ISM. We are not going to detect them. So they're hidden, they're there. But we just don't know how many. If you look at the black hole system, we measured log N log S of the 13 quiescent black hole LMXP candidates, and that's actually similar to the local black holes log N log S derived by Padilla. So if you extend this power law down to the faintest local black hole LMXP's luminosity, you get about 500 to 1,000 black hole LMXPs still hidden there. And then, like I said, 3 X-ray bursts with only 1 outburst, could be some of them. Okay, then let's skip this, but I can just talk about it. So if you take the 3 black hole transients and then 500 1,000 black hole LMXPs still hidden, you can put some nice constraint on the outburst recurrence time, which can be like 1,000 years. Okay, so if you put together 13 quiescent black hole LMXPs and then 3 transient black holes, then look at their distribution. This is how it looks like. So 3 transients, 13 quiescent black holes, and in this scale, that's 1 parsec radius. In this case, it's better to probably use the nuclear star cluster, which is also aligned with the galactic plane, and looks like they're aligned. When we fit a 2-dimensional Gaussian fit with a maximum likelihood analysis, the centroid of this distribution slightly shifted from Sagittarius star. It's here with some large error bar, and it's elongated, and its orientation is 23 degrees plus minus 13 degrees. Again, large error bar from the north, which is aligned to the NSC. Okay, but let's be careful here because the galactic center has all kinds of gas, molecular cloud blocking X-rays. So there are 2 effects. One is you can see these contours representing a circumnuclear disk. That's a very thick molecular disk. If you have X-ray sources behind it, you don't see any X-rays because of the absorption. That's number one. Number two, we have a very bright diffuse X-ray emission from Sagittarius star itself. There's a Parsamine nebula. There's an IR-13 star cluster. That's too bright to detect any fainter X-ray sources. So you can see, you can see there's really no soft non-thermal sources detected here. So I have 2 more slides. Okay. Then, so we ran the Monte Carlo simulation, assuming a spherical, 3-dimensional spherical density profile. It goes like a power law. You can see here. And then we put the 3-dimensional CND structure here, which will hide, obscure your X-ray sources. Then what we came up with this is the spherical distribution is rejected at 98% confidence level. So it's still marginal. It's not 3 sigma. Okay, so what do we learn in the future, or what's going on right now? So we are analyzing more ACSS data. We have collaborators looking at the Sagittarius star almost every day. So we have private access to the point sources as long as you don't touch Sagittarius star data. And we expect to increase the number of quiescent X-ray binaries by a factor of 3. That's huge. Okay, and then we can do a variability study to distinguish between X-ray binaries and MSPs. And then we keep doing swift monitoring of the galactic center, so we may find a new X-ray transient every 2 years. And I'd like to know the nature of VFXTs. That's kind of important because we have 9 VFXTs, and this will make a very good science case for the LINX X-ray observatory. And I will put my summary page here and take some questions.
I'm feeling optimistic after that talk, so I have my Yankees hat on. So does anyone have any questions for our speaker? And I'll ask our next speakers to start coming up, Carl and Arya.
So given all that you described in the second half of the talk, showing different spectral slopes and iron lines and some sorts of, some neutron stars and black holes, can you describe a little bit more about using the hardness ratio as an indicator of whether it's a CV or a black hole or neutron star?
Yes, so coming back to this slide, so that's a broadband X-ray spectrum of the black hole neutron cell MXV versus magnetic CVs. And then it's going back to the Munoz original paper back in 2009 or 2005. But if you look at the Chandra band, which starts from 2 kV to 8 kV, just ignore the new stuff part. And then it looks very hard, and then with the iron line. So if you simply fit a single power law to this magnetic CV spectrum, you get a very hard photon index, like 0. On the other hand, if you fit the neutron style MXP or black hole MXP spectrum from 2 to 8 K, that's again Chandra band, you get a photon index around 1.5 to 2. So that has been verified by using the actual magnetic CVs. We run a bunch of simulations using XSpec and the actual MARC simulation, putting all these template magnetic CVs and then LMXPs on the actual Chandra data, run many simulations, verifying our hardness ratio analysis is valid as long as you have enough counts, which is 100 for ACIS I case. It's a long story, which I can talk about, but even the Chandra's narrow band, you can clearly see the difference between magnetic CV and the LMXPs.
So we're going to leave it there. If you have more questions, we can discuss in this afternoon session. For any of our speakers, if you haven't been able to get into Dropbox, we can use AirPlay.
Yeah,
so.
but apparently he was able to get the Dropbox.
Okay, it's working? Okay, so, right. So we can either AirPlay or use Dropbox. Okay, thank you.
Okay.
All right. So next up, we have a joint presentation. So next up, we have a joint presentation from Carl Rodriguez and Fabio Antonini. They're going to give us a primer on dynamics of the objects that we expect in galactic nuclei. So we heard something. 5.259. Oh,
Okay.
Generate.
Actually,
So in this Dropbox, it really has to be this thing. But otherwise,
Barry, Apple, look on the keyboard.
huh?
Look on the keyboard.
Oh, how you doing?
Sorry about that. He was, yep,
I know, I've never met you.
Right here.
yes.
Oh,
There we go.
okay. So just refresh. Yeah. Fabulous. Okay, all right.
Take it away.
Yep.
Sorry about that.
Okay, folks. First up is Carl, then Fabio. Okay.
Oh, yeah, he was showing that,
All right. Hi, everybody. My name is Carl Rodriguez. I'm a dynamicist that works on dynamicist things. I'm going to do a very, very high-level introduction to just sort of how black holes sort of behave in dense star clusters. There's going to be virtually none of my own stuff. It's just going to be very, very top level, some back-of-the-envelope rate calculations and a lot of pictures. And then I'm going to turn it over to Fabio, who's going to go a little more into detail about actual predictions from nuclear star clusters for binary black holes and things like that. So the general picture to have in mind with any star cluster, this is open cluster, globule cluster, galactic nuclei, is that it's pretty easy, right, to form black holes in these things. As long as you have massive stars at some point during the evolution of a star cluster, those massive stars are going to collapse either directly or in a supernova and leave behind a population of massive stars. This happens on a very rapid timescale, right? This happens generally for massive stars on about a 10 mega-year timescale. Now, once I have these massive particles in this dense stellar environment, in this collisional environment, each black hole is going to experience many, close passages and far away passages with other objects, sort of gravitational encounters that slowly sap energy away from the actual black hole. So if I imagine that I just have some massive black hole traveling through a sea of stars with some velocity v, as the massive object travels in one direction, it's going to gravitationally attract a wake of objects towards it. And as it moves out of the way, it's going to build up a self-gravitating wake of stars behind it. And that self-gravitating wake is going to cause a deceleration to the forward velocity of the particles. An effect we call dynamical friction. By the way, I didn't make all of these slides for this talk. I had a lot of these lying around. I'm very proud of them. I don't like y'all that much. And so, because of this dynamical friction effect, essentially these massive particles are going to segregate into the center of the cluster. They're going to lose their forward velocity and end up forming this dense region of predominantly black holes in the center of the cluster. And this happens on a time scale that depends on the relaxation time of the cluster. So if I have a black hole with mass 10, let's say 10 solar masses, and my typical star is a solar mass, on average, this dynamical friction timescale, this mass segregation timescale, is going to be 10 times faster than the total relaxation time of the cluster. So even if my cluster is too big and too puffy to core collapse within the age of the universe, like say a very massive globular cluster or a galactic nucleus, mass segregation can cause us to happen on a much faster timescale. Now, once I have all these objects in the center of the cluster, right, I still have to come up with some way to form the binaries that we're interested in, and that's kind of why we're all here, right? So if I have just two objects floating around in space and I throw them at one another, positive energy in, positive energy out, there's no way to dissipate enough energy in order for this to actually form a bound system. So even if I have a huge density of objects, two-body encounters, at least in the Newtonian sense, are not enough to actually create this. What I need is some way to dissipate that excess energy and angular momentum in order to create a bound system. I need some way to subtract the excess energy from this encounter and leave myself with a bound negative object. So if I'm in a dense stellar environment, though, where the, say, stellar densities of black holes are 10 to the 6, 10 to the 8 black holes per parsec cube, you can easily imagine that I have a third interloping particle that I can actually dump that excess energy and angular momentum onto during these encounters. And just from this simple analytic argument, I can actually make an estimate for the rate at which this occurs. Because I know, just based on simple statistics and an n sigma v argument, how often I'm going to have two particles come within some certain distance of one another. And I know, based on that impact parameter, how long those two particles are going to spin, roughly at paracenter. And so I can just ask the question, for two particles that come within a certain impact parameter b, how often, while they're at that close paracenter passage, and I'm going to have a third object close enough together to participate in these encounters. And so if I do that, And this calculation, as far as I know, was I think first done by Hutt in 1985. I can come up with a pretty good estimate for the rate of three-body formation of binaries in a dense stellar environment. So if I have, what I've done here is, because this is what I work on, taking parameters, similar to a globular cluster. If I have a number density of black holes of 10 to the 5, 10 solar mass black holes, and a velocity dispersion of about 10 kilometers a second, I'll get about 100 of these per parsec cube per meteor. And we think actually this is what drives the dynamics in lower mass clusters, like either very wimpy nuclear star clusters or globular clusters. The problem, though, is if you look on the right, the velocity dispersion goes as it's 1 over the velocity dispersion to the 9th power, which is an absurd power to see in any sort of calculation. And so, like I said, for globular clusters, this works pretty well, but we're not interested in globular clusters. We're interested in nuclear star clusters, right? Which I'm somewhat asininely here representing as just a much bigger version of 47 Tuck. And on top of that, there are, in most of these cases, and in particularly in the cases we're interested in, a giant black hole in the center. I don't know what's going on with these transitions. But once you have this supermassive black hole in the center, and you have a cusp of black holes, and you have a cusp of black holes around it, your velocity dispersion increases dramatically. And so now we're looking at this case. I don't know what this thing's doing. Why you never use somebody else's computer. Now you have this case where the velocity dispersion is 1,000 kilometers a second. You're in the Keplerian potential of the supermassive black hole, and your rate of three-body formation tanks completely. So now you're lucky if you have about a 1 in a million chance, at least for these parameters, of getting a three-body formation event within the age of the universe. So that's bad. So the question then is there some way we can get around this? And what I'm putting up here now is sort of the 3 ways we think you can get binaries in dense stellar environments. The first is this three-body binary formation that I was just talking about, and that's out. What's wrong with this thing? The other option, which I think Fabio's going to talk about a little bit, is what if you just start off with a binary to begin with? We know that most massive stars are formed in binaries. We know that a lot of those, through some complicated gastrophysics we don't fully understand, are going to collapse to form compact binaries. And once I'm there, encounters with other black holes and interactions with the supermassive black hole are going to potentially allow for dynamical induced mergers of compact objects. The third idea, though, is what if there's a way we can actually create captures in these dense stellar environments? And so this actually goes back, if you look at this picture again, right, the reason I needed this third object in this particular environment is that I needed some way to dissipate that energy and angular momentum, right? In a Newtonian sense, there is no way, in a Newtonian point particle limit, there is no way to dissipate the sufficient energy to form a bound system. But but there are, of course, other ways to get rid of that energy. There's tidal interactions with massive stars. There's gas drag, like in AGN disks. And at least for the case I'm about to talk about, there's also the possibility of creating what are called gravitational wave capture events. Essentially, gravitational waves during a very close parasitic passage actually take enough energy away from the system to create a bound binary almost instantaneously. And so I can actually ask the question, what is the rate of these two-body captures compared to these three-body captures? And I get a reasonably good estimate. In this case, this goes back to a paper from Cole Miller and Melvin Davies, and they showed that for the same parameters I just showed, you get about 1 million times increase in the rate of two-body captures versus three-body formation in galactic nuclei. And the reason for that is you can get very close parasitic passages, but you don't have to deal with this obnoxious problem where you need 2 particles to come in and have a third particle also come in at the same time. You don't have to have those really low velocity dispersions. So essentially going down in the number of particles and the number of degrees of freedom gives you a significant, it basically gets rid of that strong 9th power dependence on the velocity dispersion, goes up to a much more reasonable 5.5 power dependence in the velocity dispersion. And you can start to form objects through two-body encounters. And this is why I really like this AGN disk channel, right? Because now I've reduced the dimensionality of the problem even further. I have just a single radial dimension that I need to deal with. And so it really increases and focuses the rate of these three-body captures, or these two-body formations. Add to that the fact that you have you have this gas drag and this hydrodynamical way of forming these binaries and subtracting the energy. And I think it's a really, really cool way to get around a lot of the other problems we have forming black holes and neutron stars dynamically in AGN. All right, that's what I was going to talk about. I'm going to turn it over to Fabio now, who's going to talk a little bit more about the specifics.
sorry, could you use the mic? Yeah, go ahead. Can I just remind everybody to try to use the mic because we do potentially have people coming in on Zoom? Just double click on it.
Double click. No, you have to download it.
Oh, okay.
yes, sorry.
Yeah, that's it. There we go.
Okay, so as Carl said, I will go a little bit more in the specific, and I will describe two specific channels for forming binary black hole mergers in nuclear clusters, and I will describe what type of predictions we can make for them and what they are. So first of all, when I think about galactic nuclei, this is what I think of. It's a massive nuclear cluster, a massive dense star cluster, really like a big version of a globular cluster sitting right at the kinematical and photometric center of a galaxy. Okay, and we do observe this actually in most nearby galaxies. And so the first channel is essentially what Carl already described. You start from your population of stars. The most massive stars collapse, form black holes. In the very high density regions of the core of the star cluster, where the black holes are segregated because of dynamical friction, you start forming black hole binaries through three-body binary formation. And some of these binaries that you form through this process are hard, which means that they will harden through subsequent three-body interactions, so by interacting with other stars or black hole in the cluster core. And at some point, and this is actually a big difference with respect to globular clusters, the binaries are not ejected from the systems because of the much higher velocity dispersions. They are retained inside the cluster, and they actually merge due to gravitational wave radiation while they're still bound to the star clusters, and this leads to actually differences in the properties of the sources with respect to sources formed in globular clusters. Then the other channel that we propose with Hagai Perez, that is sitting in this audience as well, is that these binaries can actually also form in the environment of nuclear clusters with a supermassive black hole. Again, there are both type of clusters are observed nuclear clusters without a supermassive black hole and nuclear clusters with a supermassive black hole, so we have to make this distinction. If you have a supermassive black hole, then the idea is that, again, what Carl briefly described is that you form stars through an episode of star formation, then the lead of Kozai mechanism leads to very high eccentricities in the binary surrounding the supermassive black hole, and because of the very large eccentricities, you induce a gravitational waving spiral. So what are the predictions for binary black hole, for the properties of binary black hole mergers formed through these two types of channels? So one way to distinguish between binary black holes formed through different channels is eventually could be looking at their eccentricities. So this plot shows our predictions for the first channel. You have the eccentricity distribution here, and the cumulative eccentricity distribution for binary black hole mergers formed in nuclear clusters without a massive black hole. And you see you have three peaks, binaries. These are binaries that are ejected from the star clusters, which represent a very small fraction of the total, about 10%. Then you have a second peak, which is binary black hole mergers that form inside the cluster, and then a third peak, which is gravitational wave captures. But the main point of this plot is to show that there is about 10 to 20% of binary black hole mergers that are formed through this channel that are eccentric also in LIGO, and the different plots are at different gravitational wave frequencies. So this is what you might be able to observe in LISA, where all binary black hole mergers, or more than 90% of them, will have maybe measurable eccentricities. And again, this is just to stress the difference between nuclear clusters and globular clusters, which is merely a consequence of the larger masses in nuclear clusters and their higher velocity dispersions. In nuclear clusters, if you look at the eccentricity distribution of binary black hole mergers formed in nuclear clusters, you see that only a few % of them might have measurable eccentricities in LIGO, so much lower eccentricities than the binaries formed in nuclear clusters. And these are the predictions that we make for the eccentricity distribution in the case of a nuclear cluster with a massive black hole, where with a guide back in 2012. Essentially no binaries in this case have eccentricities larger than 0.1, and this has been confirmed in this, I think, very remarkable paper from Zhang et al., where not only the Lidov-Kozai mechanism was included, but many other processes like two-body relaxation, resonant relaxation, and also the evaporation of the binaries due to encounters with other stars or black holes was also included self-consistently in these models. But again, you find, and this is these plots, these colors correspond to different black hole masses, and again, you find, although these models are more complicated, a similar result to what we found here. So no binaries with large eccentricities larger than 0.1, and a characteristic peak around 10 to the minus 2 or maybe 10 to the minus 3 in LIGO. The mass distribution might also be different from, we expect that also be different with respect to globular clusters. And so what I show here is the maximum mass of the black hole binary merger that is formed in our models as a function of the escape velocity from the star cluster. And globular clusters have escape velocities that are typically much smaller than 100 kilometers per second. And you see that here the maximum mass that you form is always around 100 solar masses. And these are models with different metallicity, different distributions of the initial spins of the black holes, which you see don't really affect much the results. But if you go to very high velocity dispersion clusters, high escape velocities, in the regime of nuclear clusters, you start forming much larger black holes. And these can only be formed in this type of systems. In the case of nuclear clusters with a massive black hole, here again the massive black hole really changes the dynamics in fundamental ways. Now interactions between binary black holes and singles lead to the disruption of binaries because of the very high velocity dispersions. So all the binaries that you form initially in the nuclear cluster are destroyed by these interactions. And so the only way actually to keep forming binary black hole mergers in these models is through continuous star formation. You have to keep forming to replenish this binary population near the supermassive black hole. And maybe the best way to do it is, again, through star formation that we see occurring in many of these clusters, including the cluster in the Milky Way. And so this will have a consequence on the mass distribution of these sources, because the maximum mass that you can get from a high metallicity environment of the black holes that you can get in these high metallicity environments is around 10, maybe 20 solar masses. The spins, there is no reason to expect that there would be a preferential orientation of the spins with respect to the angular momentum of the binary. So we expect a distribution similar to the distribution of binary black hole mergers that are formed in the Monte Carlo simulations of globular clusters that Carl has been performing with the Northwestern group over the last years. So a distribution that is peaked around 0, but is broad and extends from -1 to 1 if you assume that the black holes have equal mass and maximally spinning black holes. And with Adrian Hammers, we have also shown that this is true for this channel. You would expect roughly random orientations of the spins, which gives these characteristic distributions, which is broad distribution, which is peaked again around a chi effective of 0. And these are the predictions for the merger rates. They're very uncertain, but the result is that both channels should produce a number, so the number of binary black hole mergers produced by these channels should be large enough that eventually we should detect some sources coming from these channels. And what I want to stress here, this merger rate, I multiply this by 1 minus the fraction of nuclear clusters that have a massive black hole at the center, which is constrained from observations, but it is not well known. So observations show that maybe that approximately around 70% of nuclear clusters in the local universe have a massive black hole, but again, this is very uncertain. So I multiply the merger rate from this channel, in which a massive black hole is present in the center of the star cluster, by the same fraction, and also by the fraction of nuclear clusters that have that are spherical, because as we have shown recently with Cristobal Petrovich, actually the merger rate from this channel is largely enhanced if your star cluster is not spherical. And so this is the summary of what we know about the properties of the binary black hole mergers formed through these two channels.
Let's thank our speaker. So, do we have any questions for our two speakers? I'm now slightly pessimistic, so I'll change times.
In your model, do you predict more out-of-compact binaries near the supermassive black holes in the case of neutron star versus black holes?
So in this model, there are very little. Most binaries have black hole components. Actually, I would say that all of them are black hole binaries, because the neutron stars don't segregate much in the center of the star cluster. This channel is most efficient for forming binary black hole mergers, not neutron star mergers. In this channel, you would form. Also, we showed with Cristobal that the rate of neutron star binary mergers is much lower than the merger rate of binary.
But in your model, do you output the binary separation distance after these simulations? Like how close they are?
These aren't self-consistent. I mean, these aren't full dynamical models. I don't think there aren't like neutron star populations in there.
Okay.
Well, there is a component of stellar. So we use a stellar evolution code to predict the properties of the neutron star binaries, and then we evolve them in the environment of the supermassive black hole. So, but again, the rates for those type of mergers are so the fraction of neutron star binaries that you would get from our models is the same as the one that you get in the field.
Sorry, Mordecai. No time for questions. We'll thank our speakers. If you have more questions about this, please send your slides to Wednesday for this afternoon session, and we'll talk more about this summit. So thank you again to our speakers. So next up, we have Erin Cara and Chelsea McLeod, and they're going to talk to us about those gas disks. So hopefully they'll give you a slightly better picture of AGN disks than my simple model that I gave you earlier. And
Yeah, hello. All right, so I was asked to give an overview of some AGN observations and talk a little bit about all of the things that are uncertainties in the rates of of how many mergers you'd expect. So yeah, what you're really going to see from this is that with the constraints that we have observationally are pretty. There's a lot of room for learning. Yeah. So I'm going to tell you a little bit about just basics of AGN structure and size, and Chelsea's going to go into that more in depth, and I'll just go through number density, AGN fraction, longevity, spin, and disk densities, and kind of focus a little bit on really X-ray observations. I've been in the decadal, white paper zone, so excuse me if I sound a little bit like a used car salesman for X-ray observatories. But anyway, here we go. So just a basic overview. You've all seen something like this, hopefully, before. AGN, we have a central supermassive black hole at the center, an accretion disk around it, and we're talking about like on parsec scales like 10 to the minus 3, 10 to the minus 2 parsecs is the accretion disk, and then outside of that you'll have the broad line region and then the narrow line region, photoionized gas at like 10 to 100 parsecs. And Chelsea will go into a little bit more on some of the observables and maybe some of the problems that we have with some of the disk models as well. So just a little bit first on AGN demographics through X-ray surveys. X-ray surveys are a really important way of understanding AGN, because basically anything that shines above 10 to the 42 ergs per second in X-rays is going to be an AGN. You don't have to worry about host galaxy contamination. You don't have to worry about, mostly if you're looking at hard X-ray surveys, you're going to get a complete sample because you don't have to deal with obscuration effects. And so there's a really nice review by Brent and Alexander in 2015, and what they show is just a compilation. This is a paper from Ueda 2014. A compilation of the results of many X-ray surveys are showing a co-moving number density of like 10 to the minus 4 AGN per cubic megaparsec. So you can see that this changes with X-ray luminosity. And then just the fraction of AGN the fraction of galaxies that are AGN is also strongly dependent on the stellar mass of the host galaxy. But you can see it's around 0.1 galaxies host an AGN. And for much lower luminosity, lower luminosity AGN, there's many galaxies, like maybe 0.3, 30% of galaxies show some kind of AGN activity. On the longevity, this is where a lot of the uncertainty, I would say, comes from. So there's been a lot of work for many years on the mean lifetime of an AGN, how long it lasts. And you can do that by just comparing the number density or the black hole mass density to the quasar luminosity functions, and you can assume that the radiative efficiency is around 0.1, and you get that the mean lifetime for AGN activity is something like 10 to 100 megayears, and that's consistent with the saltpeter timescale. And so it's showing that really on when you look at these things on a survey perspective, on an average, that black hole growth can be explained by accretion during quasar phase. But there is a possibility that you could get, the average lifetime is something like 10 to the 7 years, but, do we know that it's consistent accretion during that time, or is it lots of like flickering, like a fluorescent light or something like that? So there was a recent paper in 2015 that looked at the BAT-selected AGN. This is a hard X-ray flux-limited sample. And what they found was that there are 5% of those BATs, those AGN, are what they call X-bombs, these X-ray bright optically normal galaxies.
And basically, they show strong AGN activity, but they don't have a photoionized narrow-line region. And so basically, you can think of that in a simple case like this, where in the evolution of this AGN activity, you have something that triggers your AGN activity, and there's a light travel time out to 100 parsecs before you see the result of that photoionized emission in the narrow-line region. And so 5% of the galaxies that of the AGN that they're finding seem to be in this kind of early stage. And so you can use that to make an estimate of the time scale of AGN activity. And you get something like 10 to the 5 years, which is much, much shorter. So maybe that's putting on the Yankee hat. It's much more optimistic for your, thank you, for your rates. But I don't know how, maybe it's too optimistic. So yeah, this is the general picture of the broadband SED. AGN are, of course, very multi-wavelength. The accretion disk is going to emit in the optical and ultraviolet. Most of the energy released through accretion is coming within like the central 20 gravitational radii of that central black hole. That thermal emission from the disk is mostly not observable. It's going to be in the extreme ultraviolet, and you're not going to be able to see that emission directly. But thankfully, we also, as I mentioned, basically X-ray emission is ubiquitous in all of these sources, and we can use the X-ray emission as a way to probe also the inner disk structure that you can't see in thermal continuum. And basically, it's because the X-ray emission is coming from what we call the X-ray corona. It's some region of mildly relativistic electrons, and these seed photons from the accretion disk will be inverse Compton scattered to X-ray energies in this corona that is really concentrated within 10 gravitational radii of the central black hole. And the X-ray corona produces this hard continuum emission that we see from 0.3 to up to like 100 keV. In addition to the continuum, that corona irradiates the inner accretion disk. So that gives us a view of what the inner disk looks like. So as the corona irradiates the accretion disk, it causes fluorescence. So you see lots of atomic features. The most prominent line is the iron K alpha line. You'll have Compton scattering off of the accretion disk. And you can use these spectral indicators as diagnostics of the structure of your inner accretion disk, and perhaps as a way to even see what an AGN disk would look like if there are gaps due to stellar mass black holes, for instance. So right now, most of our models are with just slabs, rotating slabs, constant density accretion disks. But you can see from this kind of basic model that you can use this iron K complex at around 6.4 keV to probe the innermost region. So you'll have, just from the rotation, Newtonian Doppler effects, special relativistic beaming, and then importantly, you'll have gravitational redshift because that emission in the X-ray band is coming within 10 gravitational radii of a black hole. And so you can see this is the actual data. This is an observation with NuSTAR. You see this asymmetrically broadened iron K alpha line and Compton scattering off of the accretion disk. In addition to what we see in the spectral lines, we also see that there are time delays associated with these reprocessed emission, and in this case, it's a 10 to the 7 solar mass black hole, and you see the iron K and Compton hump lagging behind the continuum by around 400 seconds, which, if you convert that to a light travel distance, is something like 10 gravitational radii. So that's kind of a good proof of concept that that these emission lines are probing the innermost regions around these black holes. So, you know, in addition, because you see this general relativistic effects, you can basically measure how redshifted your iron line is, how much gravitational redshift you're seeing to make an estimate of the spin of the black hole, which is going to change the location of the innermost stable circular orbit. And so this has been done for like about 20 AGNs so far. And this is a compilation that we put together for the StrobeX probe mission concept, which is really going to just knock this science out of the park. And what you see is in the sources that we can do this analysis with, measuring the gravitational redshift in the iron K alpha line, we're seeing many high spin AGN, high spin black holes. And that may be a selection effect because
Sorry.
those are
I'm
also
on the Zoom and I accidentally unmuted it. So pretty wild.
in there. You know, your radiative efficiency is going to increase with the spin of the black hole. So these are also going to be the brightest sources that you see, and then therefore the easiest to measure their spin. So there may be a selection effect here. But just as kind of an aside, we also see, as we saw in the first talk, broadened iron K alpha lines in stellar mass black holes as well. And in that case, we kind of see a little bit more of a range of black hole spins, but also a lot of high spin black holes. And so it'll be interesting to compare that to the results that we're seeing in the chi-effective from gravitational wave black hole binaries, and something I'd like to discuss more with the group here. And then lastly, can we get a diagnostic for the density of the disk? This one's a little harder, and maybe this is a little more speculative, but one of the observations that we see often in these spectra of reflection off of reprocessed emission off of the inner accretion disk, in addition to this broadened iron K emission line and the Compton scattering off of the accretion disk, there's also very oftentimes this soft excess, just below 1 keV, that regardless, it's a very smooth feature, and regardless of the mass of the black hole, it can be pretty well described with a thermal component of around 0.1 keV. So it's really too hot to be actually associated with the thermal emission from the accretion disk, and since it doesn't change with the mass of the black hole, it's likely not to be emission from the seed photons from the accretion disk. But there's been a lot of debate in the community as to what is the origin of this soft excess. So maybe you remember from a few slides ago that there are a slew of other atomic features expected at below 1 keV, and so it's thought that this soft excess could be due to just all of these emission lines that are relativistically smeared, and so they kind of form into a continuum. That's consistent with the fact that we see short light travel, well, we see short lags associated with this soft excess. But it could be, there are like other models where this soft excess is associated with some hot inner flow, an additional Comptonizing continuum component. But in the model where the soft excess is due to reprocessing off of the disk, perhaps you can use that as a diagnostic for the density of the accretion disk. And this is new work recent work by Javier Garcia doing showing that if you increase, basically everything that we've done so far in fitting these spectral features has been done with a constant density disk of with an electron density of 10 to the 15. But if you increase the density of that accretion disk, it does little to change the iron and the Compton scattering, but what it does change is the free heating, and that goes as the density squared. And so as you increase the density of that accretion disk, it could fit better some of the data that we're seeing where you see this strong soft excess. And Jiachen Zhang is working currently on a paper doing a compilation of these things in fitting the soft excess with these new high-density models, and is finding kind of a range of densities. So this could be a new indicator of disk density. And now I'll turn it over to Chelsea, who will go into more details on reverberation mapping. Yeah, thank you.
Okay, so just quickly, I wanted to show two observational results, basically, that show disagreement with our standard thin disk theory. Basically, the two results are that the observed disk sizes are much larger than we would expect from theory, and also the time scales that we observe are much shorter than we would expect for a steady state thin accretion disk. So just really quickly, the intrinsic, oh, there's echo. The intrinsic optical variability of AGN is on the order of 20% or 0.2 mags over time scales of months to years. And you can see an example light curve up there in the upper right panel for NGC 5548. And this optical emission, we know, contains some amount of reprocessed UV emission, and this comes from reverberation mapping of the disk, which I'll talk about in a second. And on the lower right-hand side, you see the spectrum of the type 1 AGN. So we do know about the structure of the broadline region from measuring lags between the emission lines and the continuum variability. So this is all enabled by the light travel timescale. So this is the first timescale I'll mention here. Basically, the time it takes for light to travel throughout the disk, if you can measure the response of different emission regions in the disk, you can constrain size scales. We know that from thin disk theory that there's a temperature gradient. Thank you. That was the perfect thing. Assuming this temperature profile and that the inner hotter regions of the disk irradiate out onto the cooler, more distant annuli, you can actually measure, you can constrain the relative sizes of these annuli by measuring time lags between the different bands if you monitor them monitor the source in different bands. So this is continuum reverberation mapping. And one particular study by Fasna et al. 2017 shows that by monitoring, there are a few AGN in the paper, but for this example in the upper right-hand side, by monitoring it in UGRIZ, they find that the time lags between the different bands shown by these data points are very different from the thin disk expectation, which is shown by the blue dashed dotted line right there. So this blue dashed line was predicted for the given parameters of that source, the black hole mass and the accretion rate. And results from microlensing are also consistent with this. So results from quasar microlensing also show that the absolute disk sizes of an AGN are few factors larger than what you would expect. It's also possible maybe we have the temperature gradient wrong as well. So lastly, I'd just like to mention that the timescales in general that we see for the intrinsic variability in a given band are confusing. This is because, so for a steady state thin disk, or for a sudden change in fuel supply, you might expect to see changes occur very gradually over the viscous timescale, which is shown here. And this in the optical emitting region of the disk should be thousands of years, so much longer than we can observe. Yet we do observe timescales of months and years in disks. So what's going on? Well, there's probably disk instabilities going on. This is the shortest timescale you might expect to see physical changes of the disk is on the dynamical timescale. And also then there's the thermal time scale. And the thermal time scale is about, few years. So from the observed variability of Stripe 82 quasars, we found the average timescale, characteristic timescale of quasars was consistent with thermal timescales. So that indicates maybe there's some localized thermal instabilities in the disk, and this might even imply an homogeneous disk. Secondly, I just wanted to highlight exciting new class of quasars that we are calling changing look quasars. And these objects, so they exhibit a type 1 agent with broad emission lines in one epoch, and then in the next epoch, the broad emission line goes away. And this is associated with a strong continuum change. And this happens very short time scale, so very much shorter than you would expect for an accretion rate change of a disk. So there are some possible explanations that involve accretion disk instabilities to explain this. I'll leave up my summary and take questions. Thanks.
So do we have any questions for our AGN disk speakers? I'm a bit more optimistic.
I'll just hand it to Aaron. Your question.
I guess I was just trying to say, so the optical, can some of this larger disk size be explained by the optical is just reprocess, X-rays or UV from the inner parts? I'm trying to understand, does it really mean, maybe if we get to the outer parts of the disk, we're not seeing the intrinsic luminosity of the disk at that point?
If anyone else in the room has a good answer, please, feel free to chime in. But it could be. I'm not sure about that. It could be that the disk is inhomogeneous, and that so on average the radius that you're measuring for a given emission region, it's actually it appears to be much larger because the disk is inhomogeneous.
But you're also seeing like changes in the continuum in the optical as well. Right.
You're saying you wouldn't expect the reprocess to be a continuum. You would expect it to be lines or something.
Well, because that's not there's definitely time delays of like a few days. That's what Chelsea showed on the first couple slides of that's the kind of light travel time that you'd expect from X-ray radiation of the disk. But yeah, this is sort of somewhere in between, like, way too short, way shorter than a viscous timescale, but kind of longer than what we measure in from just light travel times between where we can actually see the correlated X-ray and UV optical.
And there are some constraints from reverberation mapping of the continuum that it's the optical light is not completely just irradiated flux from X-rays and UV. So maybe, I think there's an estimate of maybe 25% of the optical flux is reprocessed emission. And indeed, in some other sources, you don't see any sort of correlation between X-rays and optical light.
You have another question? Okay. Anyone else? Silva, you were right.
Well, I'm curious, are there ones where there's both lensing and reverberation, and do they agree on the sizes?
Oh, yeah, so that's a good point. So for, there was I think there was a plan to do that, but I'm not sure if it's been done yet. I'm not sure, because maybe I haven't been paying attention, but yeah, if you can do microlensing and reverberation mapping for the same source, that would essentially give you a three-dimensional size constraint. So you get the line of sight and the projected size from the microlensing. So that would be.
I'm surprised if there aren't.
Well, it would be very difficult because usually it's quasars that are being microlensed, and quasars are much more luminous and their variability timescales are much larger. So you'd have to be just staring at it for a long, long, long time and resolving each of the images. So from the ground, at the precision that we need, that's very difficult to do. I'm sure people are trying, I just haven't heard of any. Sorry to jump in there.
Okay, folks, if we can thank our two speakers again. This is the end of our early morning session, so we're going to have a half-hour break. Please talk, introduce yourself to people. We're going to be back here at 11. Now would be a great time if you haven't already sent your slides to the various sessions that you're interested in sort of advertising or talking about something or raising a point. Now would be a good time to email your one slides to.
Or you can now Dropbox, and I'm creating folders for each session, which will be in place in about 2 minutes.
Fabulous. Okay, other than that, have some coffee. Okay, thank you. Yeah, so the
Have a room reserved.
Yeah, so basically.
And I actually think.
Oh, you were like, okay, great.
But anyways, only if you want.
I did that math like.
Think about it.
Oh, okay.
I worked with,
I can, it could be informal, because we're gonna have other talks that
I
afternoon.
was just like, wait, no, maybe. Because that was like,
You know, that
one
was
of like
right
the
around-
second, like, school board. So I was
Okay,
like,
yeah, that was around the time that I started, so it was kind
One of the
You're on for a little bit. I will be.
One of the things.
I just wanted to say.
One of them is in
Yeah, I know this now. And he's like, they're also doing spectroscopic chambers.
Oh, wow.
Get the monitoring. What are we gonna do? Internet connection will let me
Yeah, but we'll be later.
So yeah, we're going to talk about.
Yeah. Oh gosh, what I'm doing though is like the reverberation mapping.
Yeah, no, I think I should.
And I'll be honest, one of the reasons
Would you expect to see
Yeah, I'm gonna go look and see where it would be plugged in. It has to be like on the floor, cause like, look, look at the connection over there. This table's plugged in. Yes. Well, no, they don't work, cause our table isn't plugged in to the power source.
If you need me, I can probably come in at 6 morning, but that's the day before the child design.
Yeah,
How are you going to I know.
if you use the Zoom connection, over that.
Yeah. No, I can just come here and sit down and just write. Just write through.
Yeah, our table is this one, and I think now they're starting to figure out. Oh, nice. Oh, Nathan, yeah, Nathan is on. But our table isn't plugged into a power source.
Okay.
Which is, good.
Yeah, I have 5 offers right now, which is really.
So they were doing.
Yeah, of course.
Can't say that.
I don't know.
Yeah, so I,
It's all right, yeah. It's all right, yeah. Not very clear. No, just, what, 6 months, yeah. Oh, yeah. Hyperspeed. Thank you.
No, this is telescope.
Oh, yeah, I know, I remember hearing about that.
So if you take their.
Yeah, I'm thinking they're not. It's like theoretically.
Apply it, then it sort of, oh yeah, this is that. But it ended up suffering. It's sufficient.
So I've been told.
But anyway, all of this.
But yeah, right now I'm working with
What kind of day?
not he does like a bunch of
I'm trying to do it on a small scale, not a specs right now. People have tried.
Right, so like teaching them the significantly larger scale. Being there for that.
It doesn't have a killer app for this in terms of finding.
Nah, you know, I'm doing some pretty. Hey, how's it going? Okay. Nice to see you again.
Then all of us are reversion folks no matter where we are.
Yeah.
Doing
So I'm
three
gonna
basic
try to find.
ones we're looking for. But I get to be able to talk to people.
Yeah, I'm gonna put one in for Mordecai session. This one's mine, is it connected? Yeah, I'll make mine like this. Right. I mean, I was thinking a lot for putting
But
it.
no, for the
Yeah.
Spitzer, it's never gonna
Yeah, I haven't officially either, but.
I was thinking more. Because it's an Earth in orbit, stuff that's around is not necessarily.
Yeah. I wanna go snack.
Oh, okay.
So your Earth is here. So actually now we're finally got to the point where your night site is at the site where Spitzer can point. For a while there, it was night on Earth, it was not the direction that Spitzer could point at, so.
Okay, so at least you can monitor it from the ground.
Yeah, so doing the simultaneous is really. Anyway, sorry, going to.
Oh, no, we can, I'll walk out there. Oh, yeah. Yeah. Yeah, that should be, yeah. I'm gonna learn a lot.
Oh, yeah, no, I mean, this is a lot of it.
Yeah. You have to think carefully about this. I think this is one of the most Yeah, no, the letter comes after you're done negotiating. Yeah. Good.
My 5th year. I graduate this year.
Well, we can,
Yeah.
let's talk.
I just figured that out, so try to replan my whole thesis.
change of plans?
Yeah, I was gonna do 6 years, and I got close to
It's saying you made the wrong choice.
graduate early and skip a lot of
Oh, congratulations. Yeah, where is it at?
That's amazing.
Zurich.
Nice.
Zurich, did you say? Are you excited to live in Europe?
Scary. Yeah, but I'm excited for it. I think that's why it's a good decision.
Yeah.
Get out of my comfort zone a little bit.
Right.
It's only for 3 years, so.
Okay.
Apply to somewhere new and try to escape early.
Yeah, exactly. That's actually why I took it. I was like, well, if I don't like it, I have 8 months to just like decide. Yeah. And actually apply for it. I didn't apply for anything. So it's like comparing one opportunity to a bunch of all the hard decisions.
Hearing all the 50 years at Princeton complaining about job applications, I think you may have dodged a bullet
Yeah,
there.
exactly. I feel like part of the difficult part of that season is like not knowing where you're gonna go. You have like other options, you don't know if you're gonna get any, and the uncertainty. And here I was like, oh, yes or no? Okay. Yeah. What about you? What's
Fourth year. No, yet. I'm not graduating. Probably at the end of probably a year from now or so.
Yeah, cool.
Yeah, that's the plan. I'm not probably whether I'm going to a postdoc or
Yeah, I wasn't sure either.
Tough
So-
for you, really?
Yeah, until I just like randomly applied. Really, like within like 3 days.
Wow. Just,
That's awesome.
showed up and interesting.
Yeah, I just got like an email about it. Yeah.
Who will you be working with, or like, you know, what general area you were doing?
Lucha Myers, so simulations. He does a whole, he has people working on a whole scale of like galaxies or like binary black holes or antibodies. So still actually discussing it. But it is an independent fellowship, so technically, you know, there has to be some agreement. So it will be computations. Yeah. Yeah, that's
I don't know
good.
if we've met. I'm Amy.
Oh, yeah.
Nice to meet you. Yeah. Hey, Sarah. How are you doing?
Oh, hi. I was looking for you. Hi, I'm Sarah.
Hi, Rainer.
Rainer's a graduate. Cool. Where? I plenty of stuff. Like, Sarah's my roommate, but also a CCA fellow. Stuff. Yeah. I'm very tired still. I have like residual tiredness, so zoning out. Yeah. What is I mean I know it's black holes, but it's like the stellar mass black hole mergers in AGN disks is the main goal, but a lot of the talks are just on like dynamics. Oh, yeah. Okay, that seems very specific. Yeah.
It is very specific, yeah. It's actually crazy. Yeah, it's crazy they could fill a room this big.
Yeah, did I hear that right? But yeah, like my own work isn't directly applicable. Yeah, I guess so many people would be. Yeah. Is it a whole, it's 3 days? Yeah. Maybe come for the wine. When is that? 4:30. Great. I'm sure this will go overtime, but 4:30 to 5:30. And are you working on black holes?
Well, I was last year, like, I was like kind of the hosting this, spearheading it. I was a part of last year, but I didn't really anymore.
Yeah. Are you enjoying?
Except for when I get reminded that I'm supposed to like submit a paper that's half written, and then I'm like, oh yeah, definitely working on it.
Is that with Robin or something?
No, that's actually with Mordecai.
Okay.
So.
And do you like Princeton?
Yeah, for the most part, yeah. It's always kind of nice to come back into the city, though.
It's different.
I do really miss it.
Yeah.
But yeah, it's nice.
Yeah.
It's nice. They're like birds.
Oh,
Lots
but
of
that's
bird
one thing I
sounds.
always point
Yeah.
out. Like I walked by a park today and I was like, birds are chirping.
Yeah.
Birds. It's like such a big deal to hear birds.
Yeah, because they're like back and they're loud.
They're not
and-
like dying pigeons or something.
Yeah.
How big is your class?
4 people. I'm the only girl.
Oh wow.
Yeah. But of 4, so
Yeah.
it's kind of small
Yeah.
number statistic.
Yeah.
Exactly.
I was thinking of, are people giving talks or is it like discussion? There's like, there's a discussion after, is it after 3? Wait, I haven't seen
Yeah, I
it
think
here.
it's like once we do the like overview talks, there'll be some discussion. 2 more planned.
I think he's just participating in discussions later. There's 2 more talks, so 20 minutes, and then a summary of all the previous talks, and then lunch, and then discussion start. I've heard nails, by the way.
Yeah, I know, it's really cool color.
They're beautiful, yeah. I might get sick of this after a whole month, because they last forever. I really like it. It's my first time doing powder gel, which I wouldn't do again. It's like cheaper, but it's like more lumpy and weird. And it lasts for a month? Yeah, at least 3 weeks. So you can see it's like, they dip it in powder, and then they put it in, and then they dip it again. I saw someone have that done. But apparently it lasts the longest. Yeah, okay. Why is it cheaper? Seems like it takes longer and lasts longer. It took forever. I'm so tired. I think you were there for like 3 hours. I also got a pedicure, but yeah, the lady was really slow. There was this one guy there who was super fast and the best, but it's hard to get him. You have to like make an appointment.
Oh man, the other day I was running late and I had to put my laundry in so that I could change it to the dryer before going to like breakfast or whatever. And I go down there and there's like 2 washers, like there are only 4 working washers. 2 have like, 20 minutes each, 2 have like 2 minutes each. I'm like, great, it's gonna work out. So the guy comes and he's like pretty on time to move his laundry, which is always good because otherwise you have to play the whole like, do I take it out? Do I leave it in and wait? He was like pretty on time, so I was really jazzed. But then he was the slowest human you've ever met. He like, oh man, he was so slow. It wasn't like, it was like 10 a.m. so it wasn't even like it was like really early in the morning, like or something like. And he like literally 2 items of clothing at a time he would take out. He would like straighten and then walk 2 items of clothing over to the dryer, put them in. And then he would go back and 2 more, and I had to wait for him to empty 2 full washing machines this way. And it took him maybe 10 minutes. And I was just standing there being like, I'm waiting, right? Like I'm not standing with a full basket of laundry in the laundry room just to chill here.
Yeah.
It was like, I was like, this is,
It'd be like
if I wasn't so impatient, it'd be funny.
Now it's funny. Do you want to catch up for a minute? Catch up? Yeah.
Sure.
Okay. Roommates.
Fine way to phrase it.
Sorry.
It's fine.
Clearly they have some gossip that we're not privy to.
Sounds like. So you worked at for this year?
Yeah, I took a gap year between. I did my undergrad at Columbia, so I took a gap year between undergrad.
Nice. Now you're a grad student.
Yep.
Awesome.
Yeah.
Astronomy.
Yeah, exactly. Yeah, in astronomy there. No, physics is much bigger. Yeah. Yeah. Too intimate. That's.
So yeah, how are you? How do you like it?
I like it. Yeah.
Yeah, I like your there.
Yeah. I mean, it's definitely a cool place.
Yeah, what are you working on?
Well, so we do like semester projects, so I'm doing like rotations. So last semester I worked on simulating 8 jets, and this semester I'm working on Lyman alpha escape fractions from high redshift galaxies. So what do I work on? Who knows? Like, I've literally worked on 4 completely different things. So I don't know.
No. How many rotations do they have? Like a set number?
2 to 4. They're not strict about it at all. Some people will literally do it. They don't really care. So
it sounds like healthy.
yeah, it isn't. I don't know. I mean, you did had to do 2 right single year projects at Columbia. Don't they make you do that? No. You just went right in?
Just,
Who do you work with?
I work with Sabi.
Yeah. Okay, cool. Yeah. So in some ways it's kind of weird because it's like you don't know who you're working with. It's like, yeah, you have to be pretty like self-motivated. You know what I mean? Like, because it's like you're a little on your own. Like, I didn't really tell anyone I was coming to this because like who would I like? I told the person I'm working with this semester. I was like, because we usually meet on Mondays, and I'm like, can't meet on Monday. And I like told the professor who had a problem set due for tomorrow, but it was like there's very little oversight. So sometimes you can kind of feel like in the darkness, and then there's like, yeah, you like don't know who you're gonna end up working with or what you're gonna end up doing. So it's like kind of weird too. It's like, where do I invest time? Like I applied for like a plasma physics summer school, and it's like, but is that a good use of time? Am I gonna do plasma astro? Like I don't know. Like, so it's kind of weird. So, but yeah, like I chose printing because I was like excited to do different things, and like it is exciting. And then you also realize this is like my 4th new project I've started since I started doing astronomy, right? And like you realize at a certain point that like the first month or 2 of every project is identical. It's like download the software, learn how it works. Like, you know what I mean? Like start with some code, learn how it works, like. And it's kind of the most boring part of any project where you're like messing up trying to use someone else's code, or like trying to install something on a cluster and it won't install. And it's like, yeah, right? Like, and like once you get into a project, you get to do science and stuff, and like, but like, you know, the first month of a project is like software stuff, and it's like really boring. Yeah, pretty much. Yeah. So, like, yeah, but this one, I'm like, God, I'm just so sick of it. Like, learning how one cluster or another works. I mean, I guess I'm biased because I do like all computational stuff. So you don't do computational stuff. I'm sure it's slightly variations on the theme, but like,
it's the same.
It's like, yeah. So So I was like really gung ho about rotations, and now I'm like, well, there are actually some.
Oh, that's a good point.
The literature reading is kind of fun because you're like, let me learn something I don't know anything about. That's pretty fun.
If they're on the same like general field, that's useful too.
Yeah.
just walked around to something super rare.
Oh no, I'm doing something pretty random right now. I don't know, but it gives you a breadth of knowledge. I don't know. I guess I'm kind of proud at this point that I have a pretty broad knowledge base, at least computation. Once you get into observation, I don't know how useful I am, but anyway. Are we almost back? Okay. I don't want to get coffee. I'm also running.
I don't want to have to like rerun it with the new one.
Where I literally have to type in a number every 3 minutes.
Ah, yeah, of course.
Yeah. So
how about the code changes every day?
Yes. So I'm gonna. I'm on the printed cluster. Not that I'm gonna like compare.
I think they might have
just
gotten
compare
that.
how. There was. I don't have to look back to the email that you said that there were conditions that party people had.
Oh, for lunch
Yes.
noon, yeah.
Lunch. Okay,
Yeah,
made
so
condition.
I can't remember which email.
Okay.
Lunch starts at oh yeah, because he was using the plumber potential with the smooth, and all of your results is that approximation. And that was the default also for the model that you're doing, but recently changed the default. But that changed back now because I found out that the one. The potential that I put as default is not really friendly, because it is it's discontinuous. So if you get too close to it, it's going to lead to a crash.
Okay.
Yeah. So actually, if instead when you if you want to compare with what the particle per is doing, and definitely the plumber potential with the smoothing that he uses is the appropriate one. Anything else will lead to a difference because most of the torques are coming from the region very close to the orbiter.
Yeah.
And that's definitely going to matter. Oh, okay. Here's the photo.
Yes.
So then I can create a new file or load a new file.
Is working on input simulations using a mixed potential and galactic cluster.
Okay.
So I've been doing input simulations. Also, but using a much more
No, I'm giving a talk in 5 minutes.
Oh, the like I meant like this, right? The next section.
Yeah, exactly.
works.
Hey. So good to see you again. How are things going?
They're going. Pretty much. Yes, I got actually them last September. I started work. I'm not looking forward to reapplying to grad school.
Close box.
That's not a fun process for
Definitely not.
He's got tired.
Yeah, like I have to definitely.
Yeah, well, good luck. Good to see you. So, how do you like living in?
I don't live there. I commute.
Between New York and
Or
vice versa.
Well, the thing is,
So luckily this semester I only have one class, so I have to be there. Oh, and I have like this study slate, so I have to be there twice.
Okay.
And then I have the option of.
Yeah, I was in here for something else, and then I took the train down to this I was getting married, so that's the only experience I have.
Yeah.
Going down.
It's like it's weird like mentally preparing yourself to for like 4 hours that day. And if you get what you I at the very least, as long as my laptop is fully charged, I can go for that hour. Or properly charged, so I can work for
Okay. So you're, what do you do with
on the
get okay.
So that's
Okay.
like right I can't take advantage. It's just sometimes
Yeah. I'm in
Is it done? Your everything.
I'm a research scientist, so yeah. I'm just a theoretical field, so yeah. So are you with us?
But like it's like people really nice. That was my word.
So you said the market messenger. So are you also dealing with the follow-ups, the optics follow-up?
And that's really nice. And the people.
Oh, okay.
I only have positive things. Like I can't think of it. Other than the commute part, right? That's nothing to do with it's just me. That's the one thing that I'm like, ugh. But everything else is
Good. Part of Lego. I think in general, astronomers tend to be a good-ish crew.
Yeah.
But physicists.
So you expect?
But that's what I'm saying. The race.
Yeah, that's what I was gonna say.
Because I'm already.
No problem.
No, anyway,
So I don't know.
That's the population that is.
No,
it's fine. I was just like, I only need we're brothers with.
Yeah. We're family. No problem, really. Okay. Whenever you need.
So it's when you guys start, we start.
I want to make sure that it's program. This table. Oh wait, it's on. I see it. I see the lights. I see the lights.
Okay.
Oh.
Yeah. So how does it work? So somebody like detects gravity wave, I guess, and they can send out
Wait a minute.
right away, and then you get it.
Oh, this is the
sleeping or whatever you get. Then
you know what? Tomorrow, tomorrow I will bring but you'll have to like handle this today.
Okay, no problem.
Yeah, because I was like, wait, but this is now I'm looking at it like, oh, yes,
No problem.
yeah.
I guess.
okay, so it's not like you don't have Right. So you basically have to take your time, you put it down from each area or something. That helps, right? So let's say X-ray finds it.
Yeah, we shot him, it was a problem.
Yeah, you know what to do. Ice cube.
Megyek haza egy elolvadt ilyen igazából fotográfiát,
Thank you. Yeah, I think for now.
I think the light is on. So
Yeah, I think you have
yes.
Great.
Oh, Mordecai, I want to show you the slide. I suppose that I'm sending you my slide. No, I know, but it's for your session. Yes. Because I wanted this and I wanted to show it's not zero, and then this is migrating one. This is the migrating one. Yeah. So these are things.
Yeah, that's mine.
Just trying to help.
By the way,
Yeah, I don't know, that's not gonna work. No, what you have to do is get it open and, you're in the west side. So you have to download it. Then you'll get away.
Oh, I'm sorry.
have all these philosophers that have never figured out how to use logic, and so all these Word documents that look it over and over.
Somebody else.
What'd you say? Figure out a background. One more. That much longer.
I don't think we.
It's just, but you know, that's
I don't think we think that's right. That's okay. You're right. This is the bonus one stuff like something.
It's okay.
Yes. You really put it
You know what I'm talking about. And it's so funny, I just saw it constantly.
I mean, I think it's hard for me. I mean, at this point, we're maybe why don't we wait and see?
Because that's the only thing I have to, like, I'm not motivated to go.
I certainly would. At this point,
You'll be the only thing that they and to go.
maybe it's a matter of also whether
I don't know how much to admit, but there's a lot of interesting projects.
You could always go, you could go out to Wednesday. I feel it's calm early enough for me coffee to get the.
I guess it's useful
Wednesday and like lunch. Yeah, go to lunch. I'm the host of lunch.
It's the same thing that
I get food. I have to go to this week's lunch. I think the whole what was I gonna say? If you go, you should at least go to the book. But that requires me.
I'm not gonna say
Yeah.
Okay,
So I'm like, I believe it. I do. But I'm also like.
Okay, so we're gonna restart. Our next primer is going to be on disk simulation. So we've already talked about populations of objects in galactic nuclei. We've talked about the properties of the disks. Now we're going to talk about how you might simulate those disks and some of the problems that we have with that. So our speakers now are going to be Vlad Lyra and Andrew McFadden. And take it away.
Thank you very much, Barry. So, yeah, this is a primer on how to model disks. So this is the cartoon idea, right, of AGN disks that was shown also before. I would say that in astrophysics we have three kinds of disks. Right, so the first are protoplanetary disks, the other one are galaxies, and the third one are AGN. And as you can see here from this image, we do not have observations of AGN to the same type that we have from the other two cases. So even then, in this case here, these are also quite recent ones. But we've been modeling protoplanetary disks already for some time, and I hope that I thought that this model would play, but apparently it's not playing either. Oops. No.
I think it was playing here though. Somehow if I try to play from this library, it doesn't go, but from there it goes, right? So this is a model done by,
Make it big.
Make it big. Right. I'll try to make it big. Oops.
There you go.
Okay, right. So this is a model done by Mario Flock of a disk that has a magnetic field in it, so that you can see the whole disk going turbulent to the MRI. So we expected this process to also happen in the AGN disks. What you're seeing now is the magnetization of the disk, right? And the fluctuations in density. So the state of the art when it comes to modeling protoplanetary disks, I would say that there are 5 major pieces of physics that we need to model them, which is MHD, which is nowadays done in both ideal and non-ideal. The gravity of the disk, which is important when it comes to massive disks. Dust, which will not matter in AGN, but in protoplanetary disks, it does. The chemistry also, because the temperatures are low, and the radiative transfer. Now, I would highlight here the radiative transfer because that's what I would consider one of the weakest links. It is hard to do both hydro and RT in a calculation. So what is usually done is that we only do post-processing through Monte Carlo. And what you're seeing here is a planet in a protoplanetary disk. This is the 3D hydro density field that you get, and then you pass that through a radiative transfer code to get what the image would look like. To include the radiation transport in the hydro, many approximations are needed, like either FLD, flux limited diffusion, and other fields actually do ray tracing, but somehow that has not made yet to disk modeling. Ray tracing definitely would be a good avenue to move to. So these are the type of codes that one usually sees in modeling disks. So grid-based codes, Eulerian, they are quite good when you have the geometry of the flow matching the geometry of your grid, right? Self-gravity is usually hard to code, right? Because it's an elliptical problem to solve. In the past few years, have seen the emergence of GPUs, right? GPUs, they are fast, but they are limited still in memory. So CPUs, per core, they are slower, but you do not have the limitation of memory. So nowadays, we can do models with thousands or a few tens of thousands of processors, and the resolution that can be used can be up to about 1,000 points in each one of the 3 dimensions. GPU is not yet to this point, but it's much faster per core. So a recent model using 4 GPUs could do 20 orbits per hour, right? That's quite good, even though the resolution in this case was still quite low. So you can do about like 10 times less resolution, but you can calculate it much quicker. The examples of these codes would be Pluto, Tina++, the Pencil code, or Fargo.
Lagrangian codes are, I mean, one of the most well-known of these is SPH, right? Smooth particle hydrodynamics. They are quite good when you have free boundaries, as we usually have in astrophysics, right? But they are not so good to model instabilities because they cannot capture well the contact discontinuities in the flow. And also there is the fact that you are modeling, I mean, you add more particles, I mean, you have them where the density is largest. So if you want to model gaps or the atmospheres of these disks where the density is low, then you intrinsically have less particles there, right? Though it is quite good to model gravity, right? Because that's what they are mostly used for. And two examples of these codes would be the gadget code and phantom. So, and so this has been mostly about protoplanetary disks, right? So why is it that we cannot just rewrite our articles just replacing protoplanetary disks for AGNs? So I would define four main differences between the two kinds of disks. The first one is that AGN disks are completely ionized, right? Whereas protoplanetary disks are not. They are poorly ionized. I would say that that's actually a good thing because disks is one of the few problems where MHD is actually much easier than non-MHD, right? So we already know reasonably well how MHD works in disks. That's the MRI which has been modeled for decades now in disks. Relativity, it's unimportant in protoplanetary disks. Thanks. And even in AGN disks, it's really only going to matter when it comes to the inner parts, right, of the AGN, like quite close to the black hole. So if you want to model that part, yes, you must model that with GR. But if you are interested in the outer parts of the disk, then that's not going to matter so much. Now, the other bit which I would like to get to is the presence of retrograde orbiters that in protoplanetary disks we don't have them. So we have a whole theory that we are still working on in protoplanetary disks about how planets interact with the gas. They orbit in the disk, they exchange angular momentum, and then they migrate. This migration can be either inwards or outwards. We do not know yet how that works. If you have retrograde orbiters or highly inclined ones, because they are simply not there when it comes to protoplanetary disks. So the migration trap. Well, so if a torque is positive, an orbiter migrates outwards, and if it's negative, it will migrate inwards, right? So in this point here, you can see an orbiter is moving out, and from this point, it is moving in. So this point is a migration trap, right? This migration trap, thank you. This migration trap works in this way. You have here many orbiters, right, in a disk. As they migrate, they are going to converge to that point. We did that for protoplanetary disks, and as you add many orbiters, this is essentially what you get in the end. What you're seeing here is the eccentricity and the distance from the star, and here is how the distance changes in time, right? So this was crowded when it came to protoplanetary disks, even though we only have 10 orbiters there, right? Imagine now what would happen if you had 100,000, as we expect in AGN disks, right? In this case, then, we don't know exactly what would happen. I think that that's one avenue that must be explored, right, with models. Like, what happens when you have crowded migration? I'm out of time, so then I will conclude now. I will just leave the points. So if you want to ask about them after we're done with the talk, I'll pass the mic now to Andrew.
Putting on my pessimistic hat, but it's just because simulations are difficult.
They are. Let me talk about a really interesting problem, which is an accretion disk. This is just a cartoon, but of a binary at the center of a disk. And it's kind of interesting because the case of a single black hole has really been studied to death. But just putting a binary at the center changes things in really interesting ways. For this meeting, we're just going to move the binary kind of out into the disk. But you can imagine that modulo the shear of the disk on large scales, the physics may be very similar. So basically you have a binary embedded in gas, which is interacting viscously and gravitationally with the binary. And so there's some very interesting physics that happens here. So this project is rich. It's been going on for decades. There are many models and classic papers in 1D that assume angularly averaged torques on the binary due to gas. But it's kind of obvious that multidimensional effects can greatly change that picture. So there have been simulations in 2 spatial dimensions, which are already challenging because we have to run for many thousands of orbits to get into steady state. So Armitage and Natarayan did this. I worked on this in 2008. And then there's been a lot of really great work. And most recently with Zoltan Hyman, who's here, and Yeki Tang, a student at NYU, we've done some recent things that I'll show you. And there's also been recent, and this is with a moving mesh code called Disco, which I'll describe. And there's also been some recent work using their repo code as well. In addition, very recently, there's a preprint that came out last week in 3D, Newtonian simulations using Athena++. Okay, so here's the kind of old picture of a circumbinary disk. Imagine now that this is no longer circular. You're in this kind of flow of the AGN disk. And the idea is that the binary can excite waves in this gas, and that those overdensities can torque back on the binary and affect its orbit. And so the old picture was that that'll happen in kind of a self-similar fashion until the black holes start to emit gravitational waves, and then they might peel away from the gas and merge on their own timescale in vacuum. And then you're left with a single black hole. Assuming it doesn't get a kick, it just sits there. And then at a viscous time, gas comes in and lights it up. So that's something you might expect in an AGN disk as well. If there was a binary there, at first it might be relatively, it might have opened up a cavity, but over time that'll fill. So the question is, we want to understand in detail if that picture is correct. And to do this, I'm going to give you a little bit of a primer on hydro. And so the equations we are solving, we do this both relativistically and non-relativistically. It's more clear to show the non-relativistic version. And it's very simple. These are conservation laws for mass density, momentum density, and energy density. And those things are conserved if there's no right-hand side. And gravity would be a right-hand side, so a source term on the right, which I don't have here, but which we have for the binary. So the basic general form for any type of conservation law is that the time derivative of some vector of conserved quantities, their densities, are changed by the divergence of fluxes of mass, momentum, and energy that are the solution to these nonlinear coupled partial differential equations. So those are notoriously difficult to solve analytically and require solutions on computers in almost all cases. So the basic idea, just a real simple, is that this is space and time and we're in 1D. We have finite volumes and we represent each finite volume by its mass density, momentum density, and energy density. And then if we look from a time slice here to the next time slice, what we need are the fluxes of mass, energy, and momentum between the faces bounding each numerical cell. And that's what the computer does. And so they generally look like this, that let's say the mass density is upgraded to a new time by the difference in flux between the fluxes on each bounding cell. So it's very simple principle. The problem is those fluxes are nonlinear, but luckily Riemann in the late 1800s actually solved. This is one of the few exact solutions to a nonlinear partial differential equation, and it's brilliant, and we use that. So what happens is if you have what's called a shock tube problem, so high pressure on one side, low pressure on the other, and that can be used to model any kind of flow that's broken up into pieces. Then you want to know how much energy, mass, and momentum is flowing across an interface, and that solution is known. So the solution is the Riemann solution, and it's a bunch of waves. There's a shock, there's a contact discontinuity, and there's a rarefaction. These are well known. And typically for the Godunov codes that are Eulerian, so a fixed mesh, what you do is you solve for the fluxes at a fixed point in space, and you allow these waves to transport mass, energy, and momentum across your face. But what's really interesting, so in the previous talk we heard about Lagrangian methods, the fact is we actually know this Riemann solution for a face that's moving at any velocity. It doesn't have to be sitting in space. It can actually be moving. So what's happened recently is codes have been constructed based on Riemann solvers that are written on moving meshes. And this is one example. Don't know quite how to make that happen. Is there a way to click?
Yeah.
This thing?
Use the mouse. No.
Oh, this mouse, okay.
Yeah, you can see the cursor mouse right there.
Okay.
Try left clicking.
Okay, cool. This is just a sample problem showing a shear flow that may happen in a disk. And what's done is space here is tessellated using a Voronoi tessellation, which is a known unique tessellation of space. What's really cool is that this is at very low resolution and is nonetheless capturing the features of the Kelvin-Helmholtz stability. So the kind of a test problem, and this is in relativistic MHD. This is a code written by Paul Duffel. And the idea is that for disks that can be great because most of the flow is supersonic orbital motion, and you don't want to be passing energy, mass, and momentum through a grid that's fixed in space supersonically because it's diffusive and would result in numerical diffusion, which is a form of viscosity, which doesn't exist in astrophysics at the levels that would be here. So that's called TESS, and this is similar to a repo, which is used in cosmology. For disks, however, we realized that the changing shape of those Voronoi cells can potentially add noise to the solution. Not always, but if you're trying to do thousands and thousands of orbits, it can be an issue. And since most of the motion is azimuthal around the central mass or binary, we use instead a cylindrical mesh, but it's allowed to shear. So each face can move at the local Kepler speed. So the faces are moving with the bulk motion of the fluid. And that means there's much less diffusion. And so it's a cartoon of that is this. Just obviously it's a much higher resolution, but this is the idea, is that you can solve fluxes even though the faces are moving. And this allows for very accurate integration of the equations of hydro. And this gives an example for a disk, of a circumbinary disk, in the co-rotating frame of the binary. So basically, what we find is that gas does accrete. There is a cavity, but gas does accrete onto the binary and forms mini disks around each black hole. Gas is shared back and forth between the black holes, but this is a very bright source. So if there were binaries in AGN disks, you might expect accretion of this sort to be lighting up and be observable. So that might be a clue. The basic picture from the simulations we get is that there's a cavity, but it's not round, it's elliptical, it's off-center, and there's gas making it into the cavity onto each black hole. There are mini disks around each black hole. There's a lump, a non-axisymmetric feature in the disk, which speeds the disk, and this is the final picture, is that you have emission from all these components. You have a shock here, you have shocks here, you have spiral shocks in the circumbinary disk. So it should be a bright source. Most recently, this is a source that's emitting gravitational waves, so it's starting to merge due to gravitational wave emission. And what we find very interestingly is even as they start to merge, there's still gas on radial plunging orbits that stays connected to the black holes. So they keep on you'll see it speed up. they keep on accreting all the way until merger. And at the very end, you'll see the merge, and there's still gas there. So the point is that this electromagnetic counterpart won't die, as far as we can tell. It'll still be there. So there's gas at merger. Okay, so the interesting thing that we found from those simulations, in fact, though, is that the torque, the gravitational torque on the binary, depends on how you treat the sink of gas around each particle. And in fact, we found in a paper here that you have some positive, you can have positive torques on the binary. So it's not it's still uncertain, as we heard for the protoplanetary case earlier, it's still uncertain whether the torques will be positive or negative. And in fact, we find it positive or negative depending on details of the calculation. And this has been confirmed recently in papers by Miranda et al. And Moody et al. So this is an important question that we should discuss more at this meeting. Okay, thanks.
So, any questions for our speakers?
In that final model, are you using radiative transfer to understand the escape of the radiation?
In a very simple way. So we have an opacity in the disk, and we calculate the surface temperature, it's all consistently with the fluid equations. So we have kind of thermal emission from the surface of the disk.
What's your equation? Are you cooling the central disk structure, the
yes.
disks around each other?
Yes, we're solving the energy equation, and we're cooling and self-consistently heating, and we actually find, for the single black hole case, we find the Shikurin-Yaev solution. Yeah. This, by the way, is a torque map showing the subtle difference between getting a positive torque and a negative torque. It's a really detailed question. Really important one, but it requires a lot of work and to not be hasty in making pronouncements. So we're working on it.
Any other questions for?
Yeah.
Yeah.
So, I'm sorry if you showed this, but our talk is next, and so I wasn't totally focusing on the last few minutes of your talk. Apologies. Does the torque, so does the positive torque only impact a certain part of the binary coalescence? Is it go positive and then it's negative and it's positive again?
It's always fluctuating. It's like 0 and it's going like this.
Yeah.
What you have to do is average it over thousands of orbits. It's really tricky problem.
So in terms of the gravitational wave signal, this would make a kind of chirp, anti-chirp.
It could. So you'd have to smooth it over some time scale. So the question is, how quickly can it respond?
Yeah.
And that'll depend on the mass of the disk compared to the mass of the binary.
That's right.
So, but it's a really interesting dynamical problem. For massive disks, you'd have some, you need to do a live binary, which is on our to-do list. Yeah.
One more question, and then we'll have lots of time for questions tomorrow in the disc sessions. Yeah, Carl.
Just following up on that, presumably these were all circular binaries. What happens if I start off with something that's formed eccentric? It's much easier to torque at apoapsis.
Yeah, so I see, I wasn't planning on showing this, don't worry. So yes, that's what we're doing right now. This is an eccentric binary. And so we're calculating torques from these, and you're absolutely right. The torques are much larger out here, and they tend to be positive. So that's what we're finding so far. But you can get these really interesting things. People talk about tidal disruption events as flares from the centers of galaxies. You can imagine sometimes these disks go away, and then they reform. So you'll see that. So anyway, it's an interesting idea that maybe some TDEs or things like this. But yeah, so eccentric and unequal mass ratio is a work in progress. So you should keep aware of that. We should have to see.
Okay, so let's thank our speakers again. Okay, our next speakers.
I'll grab this one.
Yeah.
Are we going to grab both halves?
You know,
We're gonna do
certainly,
it.
yeah, you know, for both, I don't know.
I'm always optimistic.
Okay.
Oh, I don't want to be pessimist.
We can share that.
We win under what New York wins.
We're always winning.
Okay.
All we do is win.
Optimistic and pessimistic.
Yeah.
This might be too long.
Oh, well.
You know what to do. Hang on.
You have to read down.
Okay, so our next
on the same
speakers
slide.
are Chiara and
have to
Migrali and Richard O'Shaughnessy. And we've talked so far about populations of objects in galactic nuclei. We've talked about disks, we've talked about how to simulate them, and now we're going to look at some of the end results of what we're talking about,
The first one,
gravitational
Michael
wave
Lisa.
signatures.
Right here.
Um,
The very top, this is the end.
Wonderful.
Take it away.
Oh, yeah, okay, so I should have this one. Okay. I have to push,
I don't think you have to.
No, I don't have to push.
You may have to turn it
I turned it
off.
off.
Okay. Just turn it on.
On, yes, no, maybe?
This one's definitely working.
So hang on, give me the.
Okay,
Just use this, we can share this.
okay,
No problem.
very friendly. Okay, just
There we go.
this?
Test,
Nope.
test.
Yeah.
Because this is in.
All right,
Okay.
I'll start the 20 minutes time.
Thank you. Okay, so I think we decided that we are the ears of the elephant. We'll talk about two different ears. I'll be one of the ears, and Cal will be the other ear.
Yeah, very large ears.
Very large ears. Since we're trying to hear the signature of potentially sources coming from these AGN disks. So we're going to talk a little bit about what sort of things you can deduce about coalescing binary black holes with gravitational waves. You may have heard that this is possible, and you may have seen some of this before because gravitational waves have been observed. And now I have to do my happy dance. We've seen the coalescence of two binary black holes. I'm making a shadow that are orbiting.
Should I do the?
Okay. Impinging on a detector. I'm sorry. I'm gonna. Impinging on a detector as they get closer and closer together, the orbit gets faster and faster and faster. We're gonna coalesce, merge, and then ring down.
This may or may not be the end of the interpretive dance part.
No, we're going to do this a lot.
That's all video, right?
Producing each one of these calculations, this is an actual numerical relativity simulation, will produce a specific prediction for whether response to the detector. Repeating this, hundreds of thousands of millions of times because CPUs are cheap. Well, not really, but something like that. We can, by comparing them, figuring out what sort of source was responsible. We can infer the masses of objects and spins of both black holes. And as we'll talk a little bit about later, the eccentricity. So these are a couple of the older binary black holes. This is 151226 with an interesting spin for one of the.
Sorry, what is this plot showing?
Sorry, I'll back up. I was assuming that more people have seen this before. So these are the inferred posterior mass distributions for a couple of binary black holes. And this are for the more massive black hole and the less massive black hole. This is the magnitude of the spin. And this is the misalignment angle of the spin. So this is saying black hole 1 is probably spinning, it could be misaligned. And this one says, I don't know, maybe negative, maybe small. Does that help? Yeah. Now, and this is, looking at plots like this, you can probably see where this is going to go. Or maybe not. Now, though some things are accessible, some observables are particularly useful, not only because it's easy to measure, but also because they're preserved over long astrophysically important timescales. One particular combination that you may have heard of, this chi-effective or effective spin that came up in one of the presentations earlier, is a combination that's conserved on astrophysically important timescales. And by measuring it and looking at this distribution, we can infer something about some things that happened a long time ago. So that's great. This is all in the context of LIGO. The other ear will report shortly. But the problem is we have two ears because it's important to highlight that we have multiple ears to hear the universe. And the signals that I just described reflect the complicated nonlinear dynamics of general relativity, whose strength, nonlinearity, and nature changes over time as the signal evolves. And therefore, the nature of the information that's being encoded changes with time and with frequency. And therefore, the questions that you ask really depend on which ear you want to use. And they depend on your instruments. And even also the physics that you want to get out. I mean, there are some simple things that you can imagine doing to say, these are my observables in some naive, simplified physical scenarios. Like if everything is quasi-circular, I can come up with something concrete. But that's maybe a completely different set of observables that are appropriate for very massive black holes and describing binary black hole radiation. So what we're going to talk about a little bit instead is the physics of merger and how that you can get out the physics of the merger from the gravitational waves that you see. Now, we have a whole bunch of gravitational wave detectors operating soon that provide different pieces of the puzzle, probing different frequency spectra, and some of which can be used to go after the same sources. And it's these two that we're going to focus on right now. We should switch sides temporarily. No, under this one. The LISA side of things, LISA is will be a space-based gravitational wave detector. You should probably say
launching in 2034. Launching in 2034.
Okay.
LIGO in space.
Is LIGO in space, for those people who haven't seen. And it's sensitive to low mass, supermassive black holes of the sort that could potentially be the hosts of the things that we're interested in. But it can also capture isolated stellar mass black holes, which evolve over from LISA into LIGO. And I want, this figure in particular from Alberto Sasana's paper highlights something that's very important to see, is that this same source in this detector might not evolve at all. And it might be a pretty Newtonian orbit at a frequency that's many orders of magnitude smaller than the LIGO band. So it's largely Newtonian. You're not really seeing that much interesting relativistic dynamics. Whereas the same source over here, evolving for a long period of time, will have complicated nonlinearities where you may have access to different pieces of information. So what are those pieces of information you might have access to? Well, there's something, there's one thing that's probably apparent, is that we can say how long it took to get from point A to point B. Slowly spiraling in, emitting gravitational radiation, getting into a tighter and tighter orbit. It'll coalesce and merge and ring down. Now, the problem is, if this was all that there was, it'd be really degenerate and really boring, and we wouldn't be able to get a lot of information out of it, because we'd be really only sensitive to something that's extremely degenerate and doesn't have a lot of features. So most of the interesting things that we like to talk about are things where things get more interesting, where we have some sort of symmetry breaking process. And one of the nice things about this channel is it offers all sorts of opportunities to do the things that we love, which is make the signal complicated and fun. So that's what we're going to talk about. So one of the simplest ways, for example, to break symmetry is just have some sort of spin in the system, and have the spin misaligned with the orbit. Happy dance. Angular momentum direction, I'm beaming radiation in both directions. I'm gradually processing, so I'm pointing towards you, flashing you with gravitational waves with the right hand, away, flashing you with gravitational waves with the left hand, and away. So you'll get pulses of polarized radiation. Polarized radiation, which is cool. Now, the other symmetry breaking feature, which is important for if we're going after the sort of things that LIGO has seen so far, which is 30 solar mass plus 30 solar mass and above, those are very short mergers. And the physics I talked about previously, is what I'll comment on in a second, is something that occurs relatively slowly. This stuff is guaranteed to appear. There is non-quadrupole emission beyond the leading order, well, quadrupole, that you would expect. This is very subdominant. This is a plot versus time in GR units, mass, and some measure of gravitational wave strength. Where you can see the dominant mode is dominant, but at late times you get all sorts of fun, interesting physics with different orientation dependence. And in fact, each one of these modes has a different characteristic frequency, which is roughly m/2 times the frequency of the dominant mode, which I'm trying to illustrate here by showing the Fourier transform of the dominant mode and some of these other modes. You can see, in effect, that by looking at a fixed frequency, we're in a sense looking at snapshots of the binary at slightly different times, which can be cool. Additionally, all of this stuff arises from lots of interesting strong field physics, which by breaking symmetry gives us access to new things. And it occurs pretty often. This is a plot of the fraction of signal amplitude that occurs as a function of mass, and it increases rapidly as you go forward. I have to hurry. The other thing that we want to talk about and highlight is precession. Now, again, this varies very wildly between one ear and the other ear, as you'll see in a second. And I'll transition to the much more fun case of LISA. So when you have a binary that's sitting on its own, it's radiating left and right-handed radiation. And if it's tilted, it's radiating left and right-handed radiation. And as it's slowly orbiting, it's basically doing exactly the same thing it would be doing due to its precession as if it wasn't precessing at all. So there is some kind of modulation of these complicated waveforms. So this is what a real waveform would look like. And all this is just taking the stuff that you saw on the previous page and rotating it with the appropriate angular momentum operators. So not everything you remember from quantum mechanics, but it works in TR2. The spin orbit couplings and spin-spin couplings are standard. This is the sort of thing that you can find in celestial mechanics. In fact, the 2p spin orbits evolutions are solved, and because they're Hamiltonian, the really nice thing about the early on spin evolution is that the early time information is still encoded and sticks around all the way to merger. So potentially, there are clues about the dynamics encoded in the configuration of spins. But wait, you're thinking, you're talking about in spiral. And wait a minute, I saw those pictures of the gravitational wave protection, and there weren't that many cycles. And so it's hopeless because the precession frequency is very, very low, which is true. However, if you look at this very closely and squint, okay, I'm kidding, you can't actually squint and see what I'm about to say. The combination of modes happens to conspire such that the black hole, when it's formed a single black hole, so this is going to be my hair, I'm a little black hole, encoded in its little hairy head. It's still doing something like this, even though it's one black hole. So the post-merger oscillations get imprinted with the configuration of the spins. So there's a lot of fun things that are conceivably accessible, even if you have a high mass binary. Now, precession is wonderful because it breaks all symmetries. It gets even more exciting if you have a long duration signal. And I'm going to not talk too much about this because you were going to talk about it more in a second. In the strong field, there are lots of strong nonlinear couplings. The precession cycles are few in number, but as we said, this is what I said previously, in the extremely strong field. Okay, great.
We're good. We're good.
We're good? Yeah. Okay, I don't have to speed up. Okay. Okay. So, as I was saying, so this is what I was saying before, is that in the very strong field, there are potentially direct access to the binary dynamics, even though you have a single black hole. So even though you're looking at something that only nominally has a few cycles in it, you would think, if you see it at high enough signal amplitude, you'll still be able to pull out some clues about the binary physics. And this is for the sort of thing you'd see for a comparable mass merger. If you have any sort of mass ratio at all, you might end up with a configuration that looks like this, which is much more like the Lisa sorts, where you have extremely complicated modulation due to precession, or, I think my eccentricity slide is gone. I had a diagram for eccentricity, it's gone. You haven't? Okay, we'll. And can also happen because you have eccentricity. The orbits aren't always circular, as you saw. Sometimes they can be eccentric. And as they spiral around this eccentric orbit, as they approach the closest point of the black hole, the orbit gets gradually tilted due to the conventional effects that you might remember from studying orbits in Schwarzschild curve. Now, you might say, well, do I care? Hopefully by the time at this point in the conference, you've probably heard that you do care. That eccentricity is great. Now, why as a relativist do I like eccentricity? Because eccentric signals are long and complicated and break every symmetry imaginable. Generally, they're going to be eccentric and precessing simultaneously. And in fact, even for sources like 5914, it's very possible to measure eccentricity if it's even remotely close to being present in band. So these are incredibly rich signals from a gravitational wave point of view. I'm not going to go through all of them. Bensei is here and he can comment on his own work. But it is certainly possible to measure the eccentricity of a compact binary as long as you have enough eccentricity occurring close enough to band. So it's really an astrophysics question. If you can make it, we can measure it. Now, the problem, of course, is, yeah, this is hard. GR is hard. Everything I said before is hard. A lot of these calculations are estimates based on in-spiral only. It's really hard to get a model that has eccentric merger and rain down that's done fully self-consistently and phase coherent. Yes, yes, yes. All true. But those problems can be fixed if the science return is high enough. And I think it is.
Before I take over, can we get a round of applause for I don't want anyone to mistake the applause for me. This is definitely for you. Okay, so I'm going to talk a little bit about LIGO in space. This is Lisa. So LISA will launch in 2034, and it's had a little bit of a complicated history, but all we need to know for today is that it has all 3 arms now. NASA is a junior partner. It's an ESA-based mission, and you can find out more about this wonderful detector here. I should also mention that it has a Pathfinder mission, and the Pathfinder performed almost as well as the full LISA was expected to, and so we are very, very optimistic for the 2034 launch. I also want to mention that my bread and butter is not the elephant, but more the rhinoceros over here, but I'm also very interested in elephants. So right now I'm going to tell you a little bit about gravitational wave sources that we find in the LISA band. And so here we have baby supermassive black holes, 10 to the 5, 10 to the 6 solar masses that are merging. But for today, I think that the most interesting thing to think about are the extreme mass ratio in spirals, which are MREs, or intermediate mass black holes that are merging with either compact objects that are a few times the mass of the sun, or an intermediate mass black hole, which is again around 1,000 times the mass of the sun, with a supermassive black hole. So these are the what we're really going to look at today, which are relevant to this workshop. So Steve Drasko's image here is of one of these MRE systems. So when I say an extreme mass ratio in spiral, this is 10 to the 4 to 10 to the 7 to 1 in terms of the Q, which is the mass ratio. And so LISA can see MREs up to Z equals 1, so a redshift of 1. And you can see any kind of complicated waveform modulation from the supermassive black hole spin in these MREs. And in fact, you can have a huge number of wave cycles that are detectable with LISA here. So we expect there to be something like 10 to the 4 to 10 to the 5 wave cycles in the LISA band. With that many wave cycles, you can do really exquisite parameter estimation on black hole mass, spin, etc., all the binary parameters, except for the distance. Distance estimates are still not great. That's still around a 10% error. And that's not good considering how well you can measure all of these other parameters. The rates, of course, vary by orders of magnitude. So with LIGO, this also varied quite a lot in the early days. This is still true here until we make the first detections. And sky localization is good to a few square degrees for these sources. I should mention, John Gare has done a lot of work on this. He's not here today, but a lot of his papers are very good, and there was a recent overview by Pau here on MREs. So one idea, well, Richard and I had quite a few ideas that we got really excited about that we CC'd Varied on when we were talking about these things. And one is, can this exquisite space-time probe tell us about the gas in the supermassive black hole accretion disks? If you can measure so many of these wave cycles, the gas will modulate the waveform in the gravitational wave. And if you have a lot of these, can you actually probe that kind of physics? I think the answer is yes, but we can discuss it later. I'm also really interested in these multi-frequency observations. Now, Alberto Cesana's 2016 figure here shows the first ever detected gravitational wave source migrating from potentially the LISA band into the LIGO band. But my idea here is to say, well, what's really interesting is the time scale between leaving the LISA band and entering the LIGO band, because this can really tell us about the environment around the black hole. And I think really anything that modulates this time scale will be accessible and interesting in both the LIGO and LISA bands. So for example, gas can cause this evolution to be accelerated. It can cause it to be so accelerated, in fact, that it makes it undetectable. So there's got to be some sort of sweet spot in the parameter space where there's enough gas to make this maybe a few years instead of 10 years, but not so fast that it merges before it gets into this band and is undetectable. So I think that this is a really interesting question that we can talk about today. I'd really like to discuss this. So I also want to highlight Andrea Derdzinski's work. I'm not going to explain too much about this because hopefully she was sitting in the back.
She must be in the bathroom or something.
Oh, she's won an Oscar. So her work here, and I think all of the co-authors are in the room except for maybe Paul Duffel. So I'm really excited to highlight this here. So she's done some work on intermediate mass ratio in spirals, or IMREs. Sorry, I don't want to confuse you at all. So these IMRIs have mass ratios of about 10 to the minus 3. And again, this can be a compact object, like a black hole or a neutron star around an intermediate mass black hole, or an intermediate mass black hole around a supermassive black hole, right? And so these mass ratios are 1,000 to 1. And what Andrea and found, together with Andrew, is this effective positive torques, which I think is really, really interesting. So the gas disk can actually slow down the in spiral, which then makes everything very confusing, because the gas is supposed to accelerate the merger time scale, but then these positive torques will decelerate it, and it can be both positive and negative. And so I wanted to make sure that I had this clear earlier, because what you can eventually see is this accordion effect, chirping and anti-chirping. And I think that this would be a really distinctive signature in the gravitational waveform that we can go after. And I just said that. So the multi-frequency, again, can be detected by LIGO, LISA, and also by LISA and the Einstein telescope. The Einstein telescope is the next generation gravitational wave detector. It'll be buried underground. It has a LISA-type configuration, will be cryogenic, will do all of the things in the future, solve world hunger, as per usual. And so anyhow, so this is one of the nice images from their paper. Here, this in the middle is your black hole. This is a secondary intermediate mass black hole, and you can see it moving through the accretion disk here, but I'm sure Andrea will talk about this later. So questions that I would really like for us to discuss during this meeting are the following. So MRIs, is it possible to get a host galaxy association for these sources? Given the poor sky localization and the not so good distance estimates, is this really going to be a feasible possibility? I'm not sure. We can probe a certain class of disk where the disk is present in these AGNs. So if the AGN turns off, then you have your black hole binary system that could start flying around, right? And so actually this might be a new avenue to study the duty cycle of an AGN disk. It could be related to these rates and these detections. Also, can we constrain the timescales between the gravitational wave bands, going from LISA to LIGO? Again, anything that affects this merger timescale really could be constrained with these multi-band frequency observations. The positive torques I find very perplexing. The alliterations might make me tongue-tied because I haven't had enough coffee. But the slower merger timescales, the faster merger timescales, I'd really like to see how this plays out and what we can explore in that particular venue. And finally, Richard and I were also talking about this. We're going to find lensed AGN, which means that the gravitational wave signal will also be lensed from these sources. And that could enable us to either, well, it will definitely enable us to see further, but it might also boost the event rate of these kinds of sources. So I'll leave this up here, and we don't have to discuss it immediately. I can also send this to Bensi because he asked us to, and I didn't do it, and I'm sorry. But I would really like to discuss these things during the meeting. So thanks for your attention.
So I'm wearing my optimistic hat for O3 and Lisa, because I'm very optimistic about that, and also for Richard's dancing.
I'm very optimistic about
that. So do we have questions for our speakers about gravitational wave? I think Sabi first, and then yeah.
So didn't you just made the case for the gap filling detector on slide 18? Yeah.
Oh yes.
Gap.
This would be great.
Oh, yes.
Yes. Someone should write a white paper.
Well, in fact, I don't know. Just off the top of my head.
Yeah, come on.
I don't know that you could get there in the strain, but in terms of the frequency, this is where you could time individual millisecond pulsars if you were basically timing the hell out of them. Forgive my language.
Yeah.
With NGBLA, I don't know, white paper fever. Sorry. Yeah.
I was wondering about the positive torque, right? You were.
That's his fault.
That it showed. No. The image there, right? That it showed. Can you put again the image that it showed about that one?
Yeah.
So that's a model that in protoplanetary disks has been done since age immemorial, and nobody has ever seen a positive torque in this case. So what is actually causing the torque here then to
I defer to the authors.
So it's what I mentioned earlier. It's the sink rate. It's how quickly you remove gas to model the black hole. So in the protoplanetary case, it's just a point mass without any mass removal. So if you move mass very quickly, the torques change sign. So if you have a black hole, it's qualitatively different than a planet.
So the mass goes onto the black hole.
Oh, but the mass goes on the planet too. I mean, like.
No, but it's
not at the
removed.
same speed.
Yeah,
Not at the same speed. That's true, but
There's also
once
two
it gets-
differences in this simulation from some other planetary protoplanetary disk simulations. One is that this is being moved in at a rate given by the gravitational wave decay rate, so the planet is being moved, right?
No, but the
We're also-
gravitational wave in this case is going to be quite slow, right? The time scale for this, which would be the equivalent to type 2 migration, is about like 1 million years.
So actually, that's not.
Isn't the time
that's
scale
not
here
uh,
true.
different?
This is,
Yeah.
The inspiral rate here using gravitational waves is way dominant. It's in the end stage where the gas perturbation.
What units is that axis?
Yeah, I guess that's the question. And how close are
These are all fabulous questions for this discussion.
There are a few hundred Schwarzschild radii.
You know, we're not yet on Tuesday, but
Actually, this will be great. Just send me slides for Tuesday.
yeah, yes. So I'd like to thank all of our speakers again. Zelda.
I have to make a comment. Sorry, not scientific, but Andrew and I submitted a proposal to the NSF, and we asked $40,000 is a choreographed dancer for a
Would you do it
professional
for
version of.
$39,000?
Yeah.
I think I could. I think you were not on the panel because unfortunately it was not fun.
You didn't offer enough kickback.
If we include him,
maybe next time.
He needs a YouTube video.
Awesome. On that note, I'd like to thank all of our speakers for this morning. So thank you. Okay, so I'm the only thing standing between you and lunch. So I'll make this short. You've heard the longest talks that we're going to have at this workshop. And the idea is that for the discussion sessions that we're going to have, you should email the one slide that you're interested
Or
in.
put in the appropriate Dropbox folder.
Or put it in the Dropbox folder, but make sure the chair of your session that you're interested in knows what slides to deal with. So send your one slide to whatever session you're interested in. Email it to the.
Or more than one, I mean, people can contribute to more than one session.
Yeah, exactly. So yes, you can email one slide per session. You know, so you have 5 opportunities to share your work or other people's work or raise questions that you think should be raised. So again, the idea is that we have a interesting discussion in these sessions. The chair is going to guide the discussions, and when your slide comes up, if you can essentially talk about what it is you're going to talk about, and the chair will sort of move it along.
also be
The So I was just going to finish. So the first part of the discussion session is going to be different people talking about the stuff that we're interested in, and then the second part I want the chairs to sort of focus on things that we can use to decide what hat to wear. Right? So I'd like to know whether I'm buying a whole bunch of Mets hats for everyone in this room, or a whole bunch of Yankee hats, right? So so in the latter half of the discussion session, if we can focus the discussion on, you know, work that needs to be done to distinguish between the optimistic and pessimistic viewpoints for the session that we're discussing. So hopefully you've got a sense of the elephant in the room. You heard from the ears. We've heard from the tail and the legs. I can get you to decide which one is which. And with that, enjoy the rest of the meeting. Please go and talk. I've already been involved in fascinating conversations. I want to have more of them. So please go and have lunch and enjoy the rest of this workshop. Okay? Thank you again to all of our speakers.